Okay, good morning, class. Let me start our 18 lectures. You may come and pick up extra example in the front table. On this lecture, we will move to use the what's so-called method of virtual verb to determine the deformation of the frame. Frame have been used in many structures, especially in the crane. The frame may use the steel to build it, or you may have a frame in the elevated highway. In Lamtapong, for example, the M6. That's also for the frame supporting the superstructure of the bridge, or no, of the elevated highway. The deformation of the rigid steel frame in these pictures. Okay, we have a steel frame, and then it's subjected to the load applied at this joint, as shown in the diagram over here, by using the hydraulic jacks in order to study the behavior of this frame under lateral, okay, the horizontal load, we call it lateral load. They use the hydraulic jack and apply it at what? The frame in our study, most of it have a rigid joint or a rigid connection. So the deformation of the beam and the frame at this connection, they're going to have equal value and rotate in the same direction. Okay. And if you check for this one, there are also two vertical load applied on the top from this one. I think this one may be the simulation of the load of the top of the structure transferred to this frame. And for sure, you guys should be able to design the experiment. In the step of design of experiment for the deformation, you should be able to draw the elastic curve. What should be the elastic curve of this one? The elastic curve of this one should be the basis on the support of the frame. What the support of the frame? We know the rigid connection on both sides. This is going to be the pin, and this is going to be the pin. And then basis upon the application of the force and the joint, rigid joint. And also there are the connection over here for the study on this behavior for sure. Under the application of the force, the beam should have lateral deformation. Sorry for that one. The frame should have lateral deformation, and the lateral deformation should move. I just make it too big, okay, in this direction. Okay, if we call this A, this B, this C, and this D. If this one move by what? By V, and Bx, the horizontal displacement at point B, this one also should have the deformation for V sub Cx. And for the frame, we make some assumption. The first one, the deformation of the beam is negligible. Deformation of the beam is negligible. That means no elongation. The what's so-called axial, the axial deformation of the beam is negligible. No elongation and contraction. So basis upon that one, V sub Cx will be equal to V sub bx. Okay. Under the application of the hydraulic jack on the top of this one, on this one and this one, the load is not very large. Again, axial deformation of the column is negligible. That means what? At this point, V sub by in the vertical, we assume it to be 0. And then on the structural analysis, next term, I will show you that one going to be very, very small. It can be neglected. And also the deformation in the vertical over here, V sub Cy is going to be 0. Okay, so the point B will move to this point B prime, and point C will move to this point C prime. Basis that on this consideration of the support and of the rigid connection, the support, the connection, and the assumption of the axial deformation of the beam and the column can be neglected. The deformation of this one should be in the form of this one. We're going to have this kind of deformation for this steel column. And due to the rigid connection, you guys know that the frame will have normal angle. Before this apply of the force, the angle over here is normal. So after that, the deformation over here will keep it at the normal. Then, if you consider the column on the right hand side, it's going to be something like this one also. Okay, like this one also, like this one. And then you have what? Under this one, you're going to have the angle at the support A and support D. Coming to the support A, due to the pin support, V sub AX equal to V sub AY equal to 0. However, we're going to have this one going to be the slope, say A. And same thing occur over here. Okay, this is going to be the axis of the column. The column over here will be rotated by theta sub D, where V sub AX equal to V sub dx equal to V sub dy equal to 0. Now, we need to consider the beam of the frame. Okay, again, this rigid joint keep the angle. Then, if you do the frame, again, you should have this kind of deformation, and the angle over here keep it in the perpendicular or 90-degree angle. Now, the beam must move in a way to connect them to each other. So, for this portion, we will have this kind of deformation in order to have continuity. Now, after you do this one, and also you may have this kind of deformation, you may see this one up, okay? This one a bit down, the connection. That means the connection over here down, the connection over here, it will move this one a bit up. Okay, you can use your notepad and zoom it in. What you have over here, you have two more things over here. The reference for the column, the reference for the beam. Now, if you draw a line that tangential to this one, you may have this one, and you may have this one, and then the angle over here rotate in clockwise direction. The angle over here also rotate in clockwise direction. The slope at point B of the column equal to the slope at point B of the beam. And this is going to be theta sub B. Rotate in the same direction of what? Of this one. Okay, and again, if you prefer, you may draw the angle between this one and this one. This is for the beam, and for this one, the tangential line. This is going to be in this direction, and this is going to be theta. Okay, and another one, you got to move to point C. On the point C, we have this reference line for the beam and this one reference line for the column. And then you have the line tangential to this one, tangential to this one. You have this angle. You have this slope. Okay, and this is going to be equal for the beam and the column. We call this one theta sub C. Okay, the same also be over here. If you do the measurement, they should have this kind of deformation, and we call it theta sub C. Okay, I compare the graphic pictures and the real structure in order you guys to comprehend what happened. Again, this is going to be the slope tangential line. This is going to be theta over here sub A. And this one also, if you have the tangential line here, you're going to have this one for theta sub D. Okay. This huge experiment is very interesting when we trying to compare what we learn, okay, from what we can see in the experiment. And I should say, most of the design of the structure in our civil engineering, you should use your imaging first, okay? During the design of this kind of experiment, you got to estimate, okay, how the structure deform, what's going to be the stresses in the structure, and what's expected performance of the structure should be. This one, we have the elastic curve compared to the experiment. And now, not only use the experiment to study the frame, okay, for this one, we have fixed support over here at point A, okay. And this is going to be another fixed support. We call it point D over here. What the structure gonna behave when it's subjected to the lateral load on this one? This is going to be the same as before. Okay, we change this one to fixed support. Okay, both of them, A and D, and B and C still keep at the rigid joint. Okay, and then under the application of the force, you should be able to imagine how the structure gonna deform under this force. First, again, we come to the same point as before. We consider the support. Okay, come to this one. We consider the support of our frame. Then what we consider the connection. Okay, the connection is going to be rigid connection over these 2 points. Then you got to use your imagine under application of the force over here. Theta sub A equal to V sub AF equal to displacement at point A in Y. Okay, this is going to be different from this one. Okay, the displacement in X and Y is 0, but this one is not 0 because this is pin. Okay, and also over here is pin, but this one is fixed. So V sub dx equal to displacement dy equal to slope at d equal to 0. Okay, again, this one, number one, just consider support. Second one, consider the rigid joint. Third, you got to consider the assumption. Again, the assumption for this frame and the previous frame, they are the same. Okay, including what we have for the elastic behavior. Okay, we got to put one axial deformation of the beam is negligible, very small. Okay, no extension, no contraction, and second axial deformation of the columns, okay, negligible. Based on this two, okay, under the application of the force, this point B will change to B palm. This point C will change to C palm. You're going to have this horizontal displacement V sub Bx won't be 0 as before. And also you have V sub By equal to 0. No contraction of the column. This one, no axial deformation of the column. And then for the slope, okay, reference to vertical and horizontal for the beam, horizontal, this one, horizontal for the beam, vertical for the column. And again, if you draw the tangential line over here and over here, you will have this kind of what? Of slope. And they are equal due to rigid joint. We call it Statically. Okay. And this one, if you draw the tangential line over here and tangential line over here, and you have this kind of rotation, we call this one theta sub c, won't be 0. On the same discussion, the movement horizontal change over here, or over here, and also over here. Okay, we call this V sub Vx, we call this V sub Cx, and V sub Cx gonna be equal to V sub Bx. Okay, and this is going to be the deformation of the structure. Then connecting the line, you just draw this one. Since this one is going to be in the vertical, so the line must be in this one, and then the line gonna have the inflection point over here, and the curve gonna be in another direction, going to be something like this one, and we have this one as the point. And also for the second column, we have the curve like this one, and then we have the curve like this one. And you can see from the result of the computer program, you have this one as the inflection point, and also this one, and the inflection point occur on this one. And also if you consider this is the point A, no deformation, and over here no deformation, and over here no deformation. And what you see over here, since there is no deformation, you see the red color. That means over here the stress is very high. Okay, the stress over here is pretty high due to the fixed support. So during the design of the fixed support, most of the time you got to consider the support carefully. And you can see over here there is another inflection point. Okay, the curve just changed from downward and then move to the upward. And you can see most of the inflection point have the blue color. Okay, that means the IP inflection point we can call IP gonna have small stress compared to the other points. Okay, actually this point is supposed to be the point of joint. Okay, if you prefer. Now that's going to be the elastic curve of the rigid frame with fixed support. Okay, and let me move you a bit to more structure. Okay, now let's draw the elastic curve of this rigid frame. Okay, we have two rigid frames. Again, recall from the previous one, basis upon our discussion, we need to apply the knowledge of boundary condition. I said that's going to be the first thing. Second thing, talking about the joint, recall from this one, we support the first, and then rigid joint the second. Okay, and then you got to consider the analysis assumption. That's gonna be, that's gonna be over here, the assumption. Then you got to use your imaging, okay, to sketch, to draft, to draw the elastic curve. If you have moment like that, okay, from the previous discussion, you may say that's very tough, Ajahn. You should be able to draw the elastic curve better because the moment diagram going to tell you how the structure behave for positive moment and this one for negative moment. So basis upon previous one, you may say this is going to be negative moment. This is going to be positive moment on this one. Positive moment, negative moment, something like this one. This is negative moment. This is going to be positive moment. That's going to help you. Okay. Now, coming to our structure again, this is going to be the pin. This is going to be the roller. Okay. The joint over here is going to be rigid joint. Under application of the force, point B move to B palm. Point A move to A palm. And then we have this one and we have this one. We call this one V sub Bx. Some textbooks say delta sub Bx. And this one delta sub Ax or equal to V sub Ax. We call this technically size sway. Okay, size sway. And then again, based on the assumption V sub By equal to 0, V sub Ay equal to 0. Due to no axial deformation, V sub Bx gonna be equal to V sub Ax. Okay, so the consideration of all the displacement at point B and point B are okay. And since C is pin, okay, so we have V sub Cx equal to V sub Cy equal to 0. But due to the sideway deformation, the theta sub A over here will be something like this one. It's going to be like this one. Then the deformation of the column, going to be something sketched to be like this one. The deformation of the column. And then due to the rigid joint, over here, the angle must kept in perpendicular as before. Now, what we have is the deformation of this one gonna be in this direction, and this one you should have what? You should have theta sub A won't be 0. Now, just connect between the joint B and joint A, and you should get the deformation of this one keep in the right angle to be something like this. This is going to be the deformation of the frame, okay? Even though you don't have the moment diagram, you can do so. Now, the second one, we have the frame with 3 members. Again, as before, we consider the support pin. Now, this one changed to roller. Okay, unlike previous two, this is fixed. This is pin. Okay, this is going to be pin and roller. Again, you should consider the joint. Okay, all of this show you the rigid joint. Okay, the rigid joint over here. And then under the application of the horizontal force, you're gonna have this kind of this placement size way. Again, we call this size way. V sub Cx equal to V sub dx. Following our previous discussion, and you know V sub Cy equal to V sub dy equal to 0. Now, at point A, V sub A y equal to V sub ax equal to 0, theta sub A won't be 0. At point B, V sub B y equal to 0. However, V sub Bx won't be 0. Theta sub B won't be 0. Is different. Okay, this is for the roller and this is for the pin. Okay, then what happened? The slope at point A. Okay, following this one should have this kind of slope, and this one called theta sub A. Due to the movement of this one, the first portion of this one should have this kind of deformation. And the angle over here must kept in this way. Okay. And then what happened over here? Okay. For sure, under the application of the force, this one must move. Okay. This one must move horizontally. And this one gonna be what? V sub Bx. And then what happened? Due to the application of the force, this one should have this kind of deformation, and then the angle over here must keep in normal angle. Okay. Now, if you consider this one, you will have this one for A sub x, and if you take the moment at A, you will have this one only for B sub y, and you have this one only for A sub y. What happens is, if you cut over here, the member over here will have only axial force of what? Of B sub y. The moment equal to 0. What happens if the moment equal to 0? If the moment won't be 0, the structure will have curvature due to the moment. Okay, we have what? We have d square v by dx square. Okay, equal to m over ei. Okay, the curvature due to the moment. If the moment is 0, what happens is the column DB won't have any kind of curve. This is going to be the straight line. Okay, no curve. And then you have this one for for the roller. And then following what we have discussed, V sub Vy is 0. But you still have zeta sub B. This is going to be your zeta sub B. Okay, this is going to be your V sub dx. Now, following the discussion before, angle over here, tangential line, that's going to be zeta sub C. And for the tangential line over here and tangential line over here with reference for the reference line, we have this angle for zeta sub D dot. Okay, so what Ajahn can ask you for these two examples, Ajahn may ask you for zeta sub A over here. Ajahn may ask you for the angle over here for zeta sub B. Or this is zeta sub C, sorry. Okay, and Ajahn may ask you for zeta sub A over here. Okay, that's going to be zeta sub A, zeta sub B, zeta sub C. Ajahn also can ask you for these two, but they are equal. So Ajahn may ask you V sub Vx, which equal to V sub Ax. This is going to call size 3. Okay. And for this problem, what Ajahn can ask you, Ajahn can ask you for zeta A. Ajahn can ask you for this one, V sub Vx. Ajahn may ask you for zeta sub V, zeta sub C, zeta sub D, and these two, they are equal. Okay, and most of the time, if we have the frame, Ajahn prefer to ask you for the size 3. Okay. Any question for drawing the elastic curve? You may come to this one. I didn't clear. You just point out. Just come and point out. No. Yeah, if we project it, if I project it, let's see, try this one. If I project this one, the distance from here to here and from here to here, they're going to be equal. Okay, but we have slope over here. Okay, actually, the deformation over here is going to be the deformation here plus the deformation over here. And I like you understand the light blue going to be straight line. Okay, no curve at all. Because of what? Because the moment in this column 0. Okay, and this is used to be our midterm examination. Okay, on the very previous year, but this time you gonna focus on something like this one. Two types of the problem. Okay, gonna be what? Gonna be pin and roller. Okay, pin and roller, and I can split. Change this one to be the pin and change this one to be the roller. Put the same thing. The deformation gonna change. Okay. Now, Ajahn just change this one to be pin and change this one to be the roller. Elastic curve gonna change. The picture gonna be the same. Just change the support. Okay. And then we have the frame. Okay, over here. And as we run out of time, let me stop the first portion of this discussion first. Okay, let me move to very important section. That's going to be the procedure of the analysis. The procedure of the analysis for the frame going to be very close to what we have for the beam. Okay, it's going to be very close to each other. First, I prefer you guys to draw the elastic curve, even though I usually didn't count it at a step, but elastic curve going to be very important to let us understand the problem. You start again with the support. This is fixed support at C. And we have this one for rigid joint at B. Okay. And then we have free end at A. Now, this one should be very simple, right? Thinking about yourself, okay? If you keep your hand as the beam, and keep yourself as the what? As the column. And then somebody trying to move you, okay? And the angle over here cannot change. So when something moves, it's going to move together, right? So like Japanese people, you do something like this one. When you meet all guys, just take the respect to them. When you take respect to them, see the beam and the column must move. Now, basis upon that concept, A must move. A must move for sure. A will have this kind of movement. Again, we know, okay, we take the curve like this one. When we take the respect to the people like the Japanese one, this one gonna be curved like this one. Since this one is curved, you got to check fixed support over here. We have V sub Cx equal to V sub Cy equal to 0. Okay. And due to the curve of your body, your head must move, right? So on the top of this one, you guys also have this kind of horizontal deformation. And let's call this one V sub Bx, okay? Or if you prefer, delta sub Bx. This one may be delta sub Cx and delta sub Cy, and also over here, theta sub C must be 0. Okay, and then due to the assumption that we discussed, V sub Bx, okay, let me call it delta because they use delta. Delta sub Bx is, delta sub By, no shortening of the beam, of the column, delta sub By going to be 0. The column won't shorten. It's shortened, but it's very small. So just take it to be 0, make the problem easier. And then over here, the angle must kept in perpendicular. And since this portion has moment inside it due to the force, they have this kind of moment. Okay, so the deformation over here must be something like this one. Okay, and then due to this yellow deformation, so we have this one for delta sub Ax. Okay, this one delta sub X, and the delta sub Ax gonna be equal to delta sub Vx, and we call them size sway. Okay, or this is a movement, just call it size sway. And then what else do you have? You got to consider this one now. The vertical displacement must move up to here, and this one is going to be delta sub A y. Okay, now you may confirm the deformation of this one to be something like this deformation. And at the end of this one, you check point A to be A harm, and you have tangential line like this one. Reference it to our line passing to the centroid, okay, or neutral axis. You will have this one to be theta sub A. Now, the problem you're looking for delta sub A and theta sub A, and sometimes also delta sub AX. When you determine delta sub AX, it's going to be equal to delta sub BX. Okay, so that's going to be the whole problem. Then After you understand, you're looking forward, you come to what so-called the virtual work equation. Now, for the virtual work equation, we have what? We have external virtual work. Virtual work. External virtual work gonna occur from the what? From the real deformation. Real deformation. Talking about trying to determine this vertical deformation, call it delta A sub y. This is real. Delta A sub y occur due to the application of 10 kilonewton. By the virtual, you got to apply what? You got to apply the 1 unit load to point A in the same direction, of the displacement. Okay. Now, the assumed forces times the real displacement, we call it external virtual work. And from the principle of conservation of energy, this external virtual work gonna be equal to internal virtual work. What's going to be the internal virtual work? Okay, it's going to be the integration. Why is going to be integration? Because the beams and the column of the frame have continuous deformation. Okay, and then the 1 unit load over here gonna cause the moment in circuit for the beams over here. If you cut by x1 under application of the force, they're going to have the moment M. Okay, the moment M at this point is going to have the curvature over here. Curvature is what? Again, d square v by dx square equal to m over ei. D by dv over here. dy dx dv by dx equal to m over ei. We have what? d theta by dx equal to m over ei. d theta equal to m over ei dx. Then you have the moment with the change of the slope at this point. You get what? You get m over ei dx. Okay, and then time small m. Okay. Now, following this discussion, you will determine the moment capital M from this one. Okay, you determine the moment, the small moment M over here from this one. So the first step, determine the equation of the capital moment Mx due to the external. Okay, due to the external. So determine capital M. This is gonna be in the purple. Capital M and X. Then determine the moment due to the unit load, small m over here, small m, and then put them back into the equation. You will get the result for the displacement at point A in the vertical direction. If you get positive, the direction of the vertical displacement is going to be in the 1.0 unit load direction. Now, if you prefer to determine the slope, okay, let me put you over here. We're looking for the slope at point A. Okay, we call it theta A. This is the real thing. Theta A is real. Okay, again, you apply 1.0 unit load at point A in the same direction. Then you have the actual 1.0 unit load times the real deformation. You get external virtual work. and then it's going to be in the form of integration, okay, of what? Under this one, there is deformation over here, okay. You got to have the same equation, m over ei dx. This is going to be in the form of the change in slope. And the change in slope gonna time what? Gonna time the moment due to the virtual 1.0 unit moment over here. So virtual moment time the real change in the slope. You get the internal virtual work. Now you determine capital MX already, right? You got to determine another one, M sub theta. Let me call this one M sub theta. Okay. After you do that, just take it back, plug into the virtual work equation, do the integration, you get the result. Again, take your calculator. If you have the white one, you're going to have a bit of this advantage, okay, to do the integration. Now, let me move to this one. This is going to be the same one. We got to first draft the elastic curve. The frame, the column of the frame should have this type of elastic curve. And then the angle over there must be kept in the same light angle as we have kept over here. Then the beam have this type of deformation. This type of deformation. And following our discussion, we're gonna determine this one for what? For V or delta sub A Y or V sub A Y. Okay, and then you also may determine this one, just project this one downward. You have this deformation delta sub AX equal to V sub AX. Okay, and then the last one, if you draw the tangential line over here and then take it with respect to the horizontal line of the beam, the neutral axis of the beam, you have this one for theta sub A. Okay, and then this is going to be your theta sub A, and this is going to be your vertical displacement over here, and the last one, horizontal displacement over here. Second one, you write the virtual work equation. Okay, you may call it virtual work equation or the equation of virtual work. Which one you prefer is up to you. Okay, equation of virtual work. Now, for the vertical displacement over here, this picture will provide you with the term M. Okay, you will determine M sub X. This is going to be this term due to the application of the force and cause this kind of vertical displacement. Now, follow the procedure. Very important thing, okay, about this one. I should say about coordinate. Okay, you got to put the coordinate on the beam and on the column. Second one, you got to talking about the side convention. Okay, the direction of the moment M sub X. Okay, you determine capital M sub X. You use any kind of coordinate. Okay, you got to use the same for small m, the same for the side convention. Okay, then later we have the beam. Sorry, we have the frame. Again, you got to put 1.0 unit load at point A in the same direction of this one, 1.0. This one, you determine small m bending moment. Then just plug capital M and small m into the equation. We got the result. Now, the important step, you got to set the coordinate. Let me set the coordinate like this one. This is going to be x1. x1 start from A to B. 0 less than equal to x1. x1 less than equal to 3 meters. For the x2, you take B down to C. That's going to be from 0 over here, less than or equal to x2, and x2 less than equal to x3. That's going to be the coordinate that you use. Now, for this one, you just cut this section. Take the moment over here. Summation of the moment equal to 0. You use this kind of sign convention. M1 is going to be minus 10x1, right? Then you do the same one of this one. Let me just last this one. M1 is going to be equal to minus 10. You do by the summation of the moment equal to 0. Then you cut another one. Okay, this is going to be 3 meters, and this is going to be your x2. You use this kind of sign of the capital M2. You will use it later. Okay, then you do the summation of the moment equal to 0 is rotate in this direction. M2 rotate in this direction, and then 10 kilonewton have the line of action here, and you got to target it by this 3 meters plus 3 times 10 equal to 0. M2 gonna be minus 30 kilonewton meter. Okay, taking care about the negative side also, okay, because it's important. Now, move the point load, assume the point load, virtual point load, apply at point A in the same direction, do the same calculation. You got to have this one. Take moment over here, the M sub V1, rotate summation of the moment equal to the rotate in the same direction of this one. It's going to be negative x1. And for this one, you take the moment over here. You put this one in the same direction as before. You get the moment M2 equal to minus 3. Okay, actually, small m is going to be capital M divided by 10. Do the integration, put them together in the table. I have the table in the problem. Please fill it because I will check the answer of your calculation from this table. Okay, the equation, the sign is going to be the same or not. The length that we use based on any given coordinate is going to be the same. Also, the I. Okay, I can check the problem really easy, such as I check this one I, this one 2I. Beware about it. Okay, just check the I. The delta going to be smaller because I is going to be the divider. See, and then you do the integration. You should be able to get the result, and for sure you should be able to draw the elastic curve. So all of this only in your PowerPoint. Okay, you may practice the integration if you not really good at it. But this time, the subject of differential equation for civil engineering come, right? Helping you to be more excellent at it. Okay, more dexterous. and then this is going to be the elastic curve. Now, you got to determine the second one. That's going to be delta sub AX. Okay. Again, this come from the computer. You can see over here. Delta sub Vy equal to 0. Why? No shortening. Okay. And if you notice this one, delta sub Vx, if you measure it by your ruler, they're gonna be equal. Okay, that's confirmed by the computer result. Okay, assumption: no deformation, no axial deformation of the beam, and no axial deformation of the column for this one. Then coming into the horizontal, the capital M sub x gonna be the same. You got to put what? 1.0 unit load at what? At point A in the horizontal direction. So the second one, just park it in this direction. Ajahn, how come you put it like this one? I have an objective. If you put the direction of the unit load in a wrong direction, you will get the negative result. Okay. Now, taking this one, again, use the same coordinates. I should say, use the same coordinate of x1. Use the same coordinate of x2. Okay. And also, use the same what? The same sign convention of the moment of what? Of the moment of this M sub x. Okay, come to the point, just touch it. And then if you use the same sign convention of the moment, take the moment over here, there is no moment occur. For this one, you're gonna have the line of action of 1.0 over here. And this one is what? The same sign convention of capital M sub x. Take moment over here. This one will be equal to the moment of 1 unit times what? Times x2. Okay, that's going to be positive. Now, you get positive. Come to the point. Just plug them into this equation. You will get the result. The first term, you may put it to be 0. Okay. No, it means no horizontal displacement. Okay. Of the first term, no first term, and that is no for the beam. But the horizontal deformation of this frame is due to the deformation of the column, not for the beam. Okay, and then due to the integration, this term is 0, and you get the second term and get the negative. See, since you put the 1.0 unit load in the wrong direction, and I should say this is going to be the negative side, and delta sub S is going to be in the opposite direction of this virtual unit load. It's going to be in this direction, and then you got the result to be 3.8 millimeter. Previously, you get what? 10. Okay, for the vertical, and this one, you get it 3.8 in this direction. So, actually, you have the resultant of the displacement is going to be delta A. This one A. Change to this one A part. It's going to be square root 10 squared plus 3.8 squared. That's going to be the resultant deformation. Okay, because the displacement is going to be the vector also, and then the slope. Capital M sub x going to be the same. You got to do what? You got to put 1.0 unit moment at point A. Okay, at point A. And then you got to taking it for M sub zeta. Capital M is okay, but capital M is important because you're going to use the same coordinate and the same sign convention. Okay, it's still involved in this calculation. So the same coordinate and also the same sign convention. If you take the moment over here, you see this one plus 1 gonna be 0. So m sub theta 1 gonna be minus 1. And the same thing over here. Okay, you use x2, take the moment over here, take the same sign convention. M sub theta 2 plus 1 gonna be 0. M sub theta 2 gonna be minus 1. Put it into your equation and do the integration. You get the result. Now, the result gonna be positive because we put the correct sign for the unit moment, and then we got the result to be 135 over EI. And I should say the slope gonna be in the unit of radian. Okay, with the direction, provide me the good direction. That's half of the slope. Okay, because the displacement is vector. It has magnitude. It has magnitude. It has the direction. Okay, and it has a unit also. And then that's going to be the result of our calculation. And I should say over here, this is going to be 3.8 millimeter. This is millimeter. Again, how about the slope that's occur over here? If you like to determine the slope, okay, slope at point B, you got to have the reference line for the beam and the column, and then you also have the tangential line over here. The rotation will be from the reference to the tangential line. The rotation over here gonna be in this direction. The slope, this one gonna be theta b. What is gonna be theta b? Okay, for sure. Just take the frame and then what? Put this one, point B. You got to determine small m, and then you got to put the 1.0 unit moment over here. Then determine m sub theta and plug it back into the equation. Very simple. Okay. Now we come to the next one. Okay. And again, this next one is going to be the second form of the problem. Okay. We have first the frame with the free end. Okay. Now, what is the second form? It's going to be the form of this one, pin and roller. And Ajahn show you guys the elastic curve of this one already. Under application of the force, this point move over here. This point move over here. They are equal. Okay, that's going to be delta Vx equal to delta Ax. And then since this is pin, okay, the deformation of this one should be something like this one. Why I know this one going to be curved? Because under application of the force, there is the horizontal and vertical force, and then you can see this force gonna cause the moment capital M, and then this portion must be curved, and then what we have over here is going to be the slope over here, tangential line over here, gonna be theta sub c, and over here the angle must kept in 90 degrees due to the rigid joint, and due to the application of the force on the top, this one move and just have be in this position, so the deformation gonna be this one. Okay, and then what we have is gonna be this deformation, and then they are equal. And then there are another slope That Ajahn may ask you even the same problem. This one for theta sub A. And reference from this one, Ajahn also may ask you for another thing, the rotation of this one from the reference to the elastic curve. This is going to be theta sub B. So actually, this problem Ajahn may ask you for theta sub A, theta sub B, theta sub C, and horizontal displacement at A, which is going to be equal to at B. Okay. Now, write down your equation. Okay. You're going to determine the horizontal displacement at point A, and that's going to be the real one. You got to have a unit load for this one. Put and assume unit load. Then this one going to be external virtual. Okay, and then the one unit gonna cause what? Gonna bending moment M sub H. Okay, and the real force gonna cause what? Gonna cause the moment capital M. This is due to the actual force or real force, actual loading. Now, if you have this one, determine this one again. If you determine capital M sub A, coordinate and sign convention gonna be the same for small m. Let me take this one. You guys should determine the reaction. Okay, I won't do it. You do it by yourself. The reaction, and then thinking about the coordinate. Okay, after you get the result of this one, taking the coordinate for this one, you take x1 from A to B. This is gonna be x1. I should say that's gonna be C to B. 0 less than equal to x1, x1 less than equal to the length of 3 meters. Take the moment over here. Okay, no need for the normal force, no need for the shear. Just take the moment capital M sub x. Okay, and then summation of the moment equal to 0 over here. This one, M1 positive. This one rotate in this direction. This one produce no moment. You can see only this 10 kilonewton times x1, and then it's rotate in the opposite direction to this one. So this one gonna be 10x1. Okay, and then move to the second one. You got this one 10x1 over here. Take the cut, okay, and put this one for x2. X2 gonna move from A to B, and from A this is 0. From 0 less than equal to x2, and this one gonna be less than equal to 3 meters. Take the moment over here. Summation of the moment equal to 0 m2. Rotate in this direction, and this one gonna be 2x2. Okay, and time the distance from here x2 over 2. So plus 2x2 times x2 over 2. Rotate in the same direction equal to 13x2. You get the result to be this one 13x2 minus x2 square sin 2 cut 2. Okay, and integrate from A to B from 0 to 3. Now you get the result of capital M sub n. For the 1.0 unit load, take the 1.0 unit load at point A. Okay, in this direction, following the elastic curve, use the same coordinate and the same sign convention, determine the reaction. Okay, you got the reaction. And then use the same sign convention. For this one, we have 1.0 unit load, rotate in opposite direction. So M sub H1 going to be 1 time X1. Okay, and then for this one, take the moment over here. This force produce no moment, and then this one rotate in the opposite direction. So it's gonna be M sub H2 gonna be 1 time X2. You get the result, and then you just put them into the table and do the integration carefully, and you get the result of 5.2 millimeter. And I should say this is going to be equal to delta sub B H or so. Okay. And for the other thing, I just ask you guys to go back and determine the other thing else, such as determine theta sub C, theta sub B, and theta sub A. And I should say this is going to be the same. Okay, the same. And again, don't forget, knowing the shear diagram and moment diagram, if I ask you, you should be able to. Okay. And then the curve like this one gonna be something like this one. See, this one gonna be a curve. And this one gonna be curve like this one. Okay, it's gonna be curve like this one, following the moment diagram. And what's gonna be the answer for the slope at A, B, C? I already told you about the delta sub dx over here. And I should stop my presentation over here. We run out of time for the Zoom. Okay. Okay, let's take 3 minutes break. We come back at 4. Let's start our third section, and on this one, I should show you about what I already provide you the extra example. I will provide you more video clips on this example, and I will take a picture and post it for you. And you may see we use the same frame, but you may see the modification of the loading on this one. If I won't put it in this video clip, there are video clips in previous years. Yes, okay, you may go to this one. And this one for the frame with the free and the fixed. And again, the second type, this one I already lecture you, but Ajahn ask you guys more about the slope at point B. And that's quite the same problem. Yes, quite the same problem, but sometimes Ajahn just ask you more. Okay, this one, I should have it in the video clips. And then we have, this is going to be, again, thin and roller. Before that, fixed and free. And this one, I already show you guys how to draw the elastic curve. We also have this video clip on the determination of the deflection at point B. Okay, Chai asked me about this one. Okay, you have video clips asking horizontal displacement at B and also at C. Actually, Ajahn can take this problem and ask you about theta A, ask you about V sub DH, those kind of things. Okay, the problem would be the same, but the question gonna be different. Now, we have this one in the for sure. And also, I just provide you guys, not only this one also, this like a 3 or 2 years, okay, examination after the COVID. This one, we also have, after I teach my students on this one, I ask them on this one. That's gonna be much different, right? Okay. And then For some very different year, I also have this one, but I didn't put the inclined column into the problem for many years already. But this one also I have changed it in the past. Now, let me take you to this one. It's not that much different from the frame that I provide in the PowerPoint, but for this rigid frame, it has extra member on the back of this one. A is fixed and C gonna be rigid connection. And this one subjected to 5 kilonewton per meter. I just changed it. On last year, I asked the problem with 10 kilonewton per meter. And then I also changed this one. I remember that's going to be 100,000. I just change this one to 10,000 and then determine what? Determine the vertical displacement, horizontal displacement, and then the slope, okay, at what? At free end of point D. You see this frame, okay, the portion CD is longer than the portion BC, subjected to the same load. So the frame should move downward from D, not from C. Based upon you have that information, and this is fixed, okay, and the deformation should be something like this way, right? And then if it comes to this one over here, it should have the what? The normal angle or 90 angle since it is rigid joint. And again, CD subjected to 5 kilonewton per meter. CD has the moment, so this one should move something like this one, and also BC subjected to the moment, so it should have this kind of deformation. Now, what you guys should have is what? The deformation of the structure. And I should say, you have this kind of horizontal, you have this kind of vertical, and this vertical is going to be what we're looking for, delta sub dy, and this one going to be delta sub dx, this delta sub dx plus dy, and also this one going to be the slope, okay? If, okay, I'm going to use these pictures for our midterm examination, what Ajahn can do, Ajahn can ask you again for this one, what's going to be delta sub bx, and this one, what's going to be your delta sub by, and also over here, there is the slope, and this is going to be your theta sub b, okay, the deformation of the structure. And then Ajahn also can ask you more, okay, C change to C palm, there is the deformation over here, that's going to be delta sub C x, and also Ajahn may ask you about the angle over here, okay, the rotation with respect to this one, okay, and for this one, in this one, and for this one, all of them, okay, gonna be equal, and call it theta sub c, okay. That means the same picture still be can be in our midterm examination, and if you have time, you may try to determine the author deformation. Now, following this one, just go to the equation of virtual work and for the equation of virtual work, we have external virtual work is going to be equal to internal virtual work. And again, following the concept, what we have, we got to put the virtual load and virtual moment to our problem. Let me put this way. This is going to be our problem. That's going to be 1.5 and 2.5 to be 4. Okay, that's going to be this is going to be B, C, D, and this one going to be 2.5. Okay, it's going to be 2.5, and it's going to be here. Okay, for the first one, we're looking for vertical deflection at point D. We're gonna put the 1.0 unit load, and we should say this 1.0 times the deformation over here, delta sub dy, and it's gonna be equal to integration the moment due to the 1 unit load. Okay, I should say m sub v or m sub y whatsoever. Okay, and then the real load going to cause the real deformation, gonna cause the theta. Okay, and we won't put it. We put it into capital M and over EI dx. This is going to be our first problem. Okay. Now, for the second question, do the same thing. Okay, you just draw the frame. Now, the frame is gonna be this one. Take this one and then 1.5 centimeter. We have this one for 2.5. We have another frame. For the other frame, we're looking for what? We're looking for delta sub dx. So, basis upon this one, just put at point D. This is going to be the direction. Put the force of 1.0. Now, you have this one to be 1.0 times delta sub dx equal to integration. Okay, this one provided with the m sub v. This provided with the m. Let me put it over here. M sub h. This one provided with m sub v. So m sub h, and then thing gonna be the same. M over ei dx. Okay, and the last one we looking for the slope. Okay, let the slope over here gonna be theta sub d. Basis upon this one, you draw another frame. Okay, and that's gonna be 1.5 and 2.5, and then another 2.5. You have another frame at point D. Provide with the moment 1.0 unit. So that's going to be 1.0, and then theta sub d, and then equal to integration. And for sure, this one will provide you m sub theta. So m sub theta times m over ei dx. Okay, that's gonna be the whole problem, and the main thing gonna be determining m. So our very first step, we analyze the frame for m sub x, Now, to analyze it, you got to select a proper coordinate. Okay, you have three members, so you're gonna have three coordinates. So what will be your coordinate? It's up to you. Okay. And most of the time, this one gonna be easier. Just put this one to be x1. So 0 less than equal to x1. x1 gonna be less than equal to 1.5. That's gonna be from B to C. Okay. And then following this one, you may take the second one, like this one gonna be x2, and you're gonna use this for every small m determination. That's gonna be 0 from less than x2 less than 2.5 meter, and that's gonna be from D to C, from D to C. And the last one is up to you. You may take from C to A, or you may take from A up to C. That's gonna be x3A till what? Till C. And that's gonna be 0 less than equal to x3. x3 less than equal to 2.5 meter. And the coordinate gonna cover all the determination of the bending moment. Now, let me move to the next one. Based upon this one, you do the calculation. Let me take it to the free body diagram of this one. That's gonna be A sub y. And we're gonna have this one to be A sub x. Okay, and we have this one for our M sub A. And based upon this one, summation of x sub x equal to 0, A sub x gonna be 0. And then following this one, summation of the moment at A equal to 0, and take the direction like this one to be positive. Okay, we have what? We have M sub A rotate in this direction. M sub A rotate in this direction. And this one will provide us with the resultant force of what? 5 times 1.5. And we have the line of action over here. And the distance from here to here is 1.5 divided by 2. This is 1.5 divided by 2 plus 5 times 1.5 square divided by 2. And in the opposite direction over here, we have the resultant force 5 times 2.5. And the line of action is over here. And from here to here is going to be 2.5. 2.5 divided by 2 equal to 5 times 2.5 and times 2.5 divided by 2. Okay, you should get your M sub A. M sub A is going to be equal to, I got it to be 10 kilonewton per meter. That's going to be 10 kilonewton per meter. And then the last one, summation of f sub y equal to 0 upward is positive. And then a sub y equal to all the forces 5 times 1.5 plus 2.5. That's going to be 4. That's going to be 20 kilonewton. This is going to be 20 kilonewton. Now, you should start by cutting this portion. Okay, and then provide the sign convention of what? Of capital M1. This is going to be capital M1 is both with the shear and the N also, but M1 is more important. So basis upon this one, summation moment equal to 0. You have this one for M1. So M1 rotate in this direction. You have this one for 5 times m1, and the distance is going to be x times 5. This is 5 x1, and this is going to be x1 over 2, and it's rotated in the same direction. So m1 plus 5 x1 times x1 over 2 equal to 0. m1 is going to be minus 2.5 x1 squared. Okay, and that's going to be our first one. Then you take this one for the m2. Take this one, cut it over here, subjected to the loading of 2.5, and then depending on you use the sign. Okay, if you use in this direction, you got to use it all the way for small m. This is m2. Summation moment equal to 0. Take this one positive, and this one gonna be 5 times x2, and m2 plus 5 times x2. The distance from here to here is going to be x2 over 2 equal to 0. So capital M2 is going to be minus 2.5 x2 squared. Okay. The last one going to be this one, and we have this to be 0. We have this one to be 20 kilonewton, and we have this one to be 10 kilonewton meter. And then you may put this one. Where is my black color? Where is it? Okay, it's over here. It's up to you. Let me took it over here from M3. Take the moment over here to be 0, and M3 plus 10 to be 0. M3 gonna be minus 10 kilonewton meter. That is for capital M. Okay, and then you got to move to this one. To determine this one, you start second step, analyze the frame. For this one, M sub V. Okay, move this one up. You got to determine the reactions. Yes, you got to determine the reaction, and based upon this one, I put this in. This is not beautiful. Take this one out, and also take this one out. You guys should have the reactions over here of what? This one gonna be your A sub Y. And again, this one gonna be your A sub X, the same sign convention. And this one gonna be your M sub A. Okay. Following this one, summation of X sub X equal to 0. This is 0. Okay. And summation of F sub Y equal to 0. A sub Y to be 1.0. Okay. If you take the summation of the moment over here to be 0, take the moment over here to be 0. This is gonna be 1. Over here, 2.5. In the opposite direction, this one gonna be 2.5. Okay. Now do the same thing. Cut the first one over here. Okay, the same one as this one, and this one gonna be M sub V1 equal to 0. No need to do the computation, it is 0. And this one, cut this one. This is going to be our x2. Okay, this is going to be our x1. And use the same sign over here, M sub V2 due to this 1.0 rotate in the same direction. This is going to be minus x2. Okay, in the same direction is minus. The last one, we have this portion for x3, and we have this 2.5 in this direction. We have 1 in this direction. Use the same sign over here. This is going to be m sub v 3, m sub v, okay, m sub v 3, and you can see is rotated in the same direction of 2.5 kilonewton. So m sub v3 is going to be minus 2.5. Okay. Now, third, you go to the third one. Okay. Compute this one, delta sub dy. Delta sub dy 1.0 delta sub dy equal to. Now you do the integration. The first one, integration of capital M1 and small m1. This one you should get it to be 0. Okay. Second one, you do the plus integration. Second one is over here from 0 to 2.5, and you have m2 over here minus 2.5 x2 squared, and this one gonna be your minus x2 dx2 over ei. Okay, ei. And the last one we have this m3 plus, okay, integration for this one from 0 to 2.5, you have capital M3 to be minus 10, and this one gonna be minus 25 dx3 over ei. Okay, and then following your integration, you should have the first one 0, the second one, this one plus 2.5 x times q plus 2.5. You integrate x to q, gonna be x to power 4 divided by 4, and then ei. You integrate from 0 to 2.5. Okay, and then the last one plus. This is gonna be positive 2.5 times 2.5 times 10, right? X3. This is x. This is gonna be 1 time this one is gonna be 2.5. 2.5. This one is correct. Integration of this one is correct. Integration of this one. This one gonna be 250. This one gonna be 250. Due to the integration, it's gonna be x3, and then that's gonna be from 0 to 2.5. Okay. What did you get? You should get the first term. Now it's gonna come to be your calculation. The first term gonna be what? Just take it. I'm not sure. And then that's gonna be divided by ei. Okay. That's gonna be what? 250 times 2.5. No, this is what? This is 10 times this one 2.5. 10 times 2.5 is going to be 25. Sorry for this one. And the total is going to be plus 86.914. Okay, and it's positive. That means the direction is going to be in this direction. Okay, and then you got to have this one to be 86.914 divided by EI 10,000 and that's gonna be 8 point it's gonna be times 10 1 2 it's gonna be 0.86914 10 minus 3 meter right it's gonna be 8.6914 10 minus 5 10 minus okay that's gonna be very small 8 0.87 millimeter downward it's gonna be something like this 0.869 if you prefer okay that's to be very small that's going to be delta sub dy for this one okay and you may try to do the other okay you should get delta sub dx equal to 31.25 EI in this direction and also you should have theta sub d equal to 38.02 divided by EI in this direction. Okay, we don't have much time for this one. Okay, let me take you to another example. Okay, let me take you. We have only for 5 minutes. This problem have two members and have equal or constant fractional rigidity. The value of E is 200 gigapascal. I gonna be 6,010 power 6. This gonna be the frame subjected to only 40 kilonewton. This is important. Under application of the force, what's going to be the elastic curve? Okay. Under the application of the force, you're going to have A sub X for sure. This one rotate this way. This one going to have the rotation of this one is going to be D sub Y and the force over here, A sub Y, no vertical force. A sub Y going to be in this direction. Okay. Under application of the force, A must have some rotations. Okay. Due to the pin, this is the pin. It have rotation of this one to be theta sub A. And then the one over here must have this kind of deformation. Okay. If you have this kind of deformation, this is gonna be delta sub CX. And if delta sub CX equal to 1.8, okay, centimeter over here, it should be 1.8. And you should have this is as your roller, okay. And then the deformation of this one must kept in this perpendicular and the deformation of this one should be something like this one and I should say the delta sub dx is going to be delta sub cx and it's going to be in this direction and over here you're gonna have this one for theta sub d and again over here you draw the tangential line for the frame draw the tangent line for the frame you should have this one. Oops. From this one this is gonna be theta sub c. Okay, the problem asking you for the slope at C, okay, it's going to be this one and horizontal force at D, that's going to be this one, okay. Again, you just write the equation of virtual work, the equation of virtual work the external work is going to be equal to the internal work, and then you got to draw two more pictures. Okay, this one going to provide you capital M sub X to determine this one. Draw this one for 36 millimeter. This one 15 is going to be 30 millimeter. Okay, and then you have this one 9 and 6. You got to have this one to be point B, to be point A, C, and D. Now this is pin. This is roller. To determine horizontal force at D, you got to put force over here of 1.0, and then 1.0 produce the deformation delta sub df is going to be equal to the integration of what? This one you will have m sub h, if you said m sub h. Okay, this one m sub dh, m sub dx, okay, x, m sub dx, and then have m sub x dx over ei. That's it for this one. Okay, and then you should draw another picture. 36 millimeter. This is C, this is D, and this one 30 millimeter, and then this is pin, this is roller. Now slope at C, you got to put the 1.0 moment, and then it's gonna have the slope at C. Okay, let me put this one to be theta sub C times theta sub C is going to be the integration of what? This one due to 1.0 produce this one small m c theta. So small m c theta times m sub x dx over ei. Then the process going to be easy, right? Compute for capital M sub x. Okay, but I should say you got to use the same sign convention. For this one, there is the point load over here. I should say you should use this one as your x1. 0 less than x1 less than equal to 6 meter. Okay, and then after that, you may use another one for this one for x2. Now, x2 gonna be from B to A. 6 less than equal to x2. x2 less than equal to 15 millimeter. x2 is noted, okay, due to the point load at the middle length of the member. Noted. I said noted. Note, this is important. Okay, and then another one. If you cut it over here, you may say this is going to be your x3. Okay, and then determining the m sub x gonna follow this kind of coordinate. Okay, and 0 less than equal to x3 less than equal to 18 millimeter. This is from D to C. This is from A to B. This is from B to C. Okay, then I will take the picture and post it for you guys to do the practice. Okay, and that's it for today. Any question? No question. Thank you very much for your attention.
we are going to study the analysis of rigid frame as shown here. This frame have the rigid support at A and the rigid joints at B and the free end at C. Under the hypothesis, you may imagine something that since the A is fixed, so when the A is subjected to the load like that, this point gonna deform like this, okay? And at the same time for the beam, when it's subjected to the point load, it's going to deform like this. So in combination of this, we will have the deformation of the frame like this, the first one, and then we may have this one is going to be the fixed, okay? When it's fixed, that means what we have is the V sub A H equal to V sub A V and theta sub A all are 0. Okay, and when this one is for the rigid joint, this is rigid joint. What we have for rigid joint is the theta sub B of the beam. Okay, theta here for the beam is equal to theta B for the column. What we are doing is this one is going to defect, for example, to this, and this one gonna have the shape something like this, and this one gonna be the fix, okay? And then when it's alive here, this portion will take the normal angle, 90-degree angle as before, and then this portion will curve like this, and then if this one is the line that's passing the centroid of the frame, okay, and this one move for this, and you may understand that due to the beam have no axial deformation, so this is going to be what this is going to be like 9 millimeter. So this is going to be like 9 millimeter. It's going to be like this, okay, and this one going to have some deformation, something like this, and this is going to be have some curve like this, and this is supposed to be the preliminary deformation of this frame, okay? So in this frame is about 3.5 centimeter, so it's going to be 3.5 centimeter, so it's going to be alive about here, and this is going to be the deformation of this beam, and we may say this is going to be the V sub C horizontal, this is going to be sub C vertical, and also they are supposed to have the slope at this point. This is going to be, this one is the theta sub C. This is a primary graph of the elastic curve, okay, and we will refine this elastic curve after we determine the horizontal deformation, the vertical deformation, and the slope, okay. And what we have is under the method of virtual work, we have the first one that's going to consider is the virtual work equation. Under virtual work equation, what we need to do is, they said the external virtual work, the external virtual work virtual work need to be equal to the internal virtual work So where is the external virtual work? External virtual work you can determine by putting the assumed unit load, okay, to the point that you are looking for the deformation. Now we consider point C. So since the vertical deformation is like this, so we got to put the 1.0 assumed force to be here, and what we have is 1.0 force will time this deformation, so will time this real deformation. Assume force, real deformation, so external virtual work, okay, is external because it is external force, and this is also external deformation, so force time displacement is work, and then it's gonna equal to what have under this applied force, this beam will have the moment inside it. The moment will bend, okay, will bend this frame into the shape like the inelastic shape, and this also will produce the moment, let's call this m sub vertical, okay, and what we have is the 1 unit force produce m vertical, so this one m vertical, and it's gonna time the curve, okay, and we also have the elastic beam theory, in which we have the curvature is equal to m over ei, that is the curvature, and we also have the slope of what? The slope of dv by dx is equal to theta, so we rewrite this equation into the d by dx, and another term there is going to be the dv by dx, and it's going to be equal to m over ei. And now what we have is d theta by dx is m over ei, and then the d theta is equal to m over ei dx. That is the curvature of this beam, okay, the slope of this beam, okay. Actually this one must time d theta, the force time linear displacement, the moment time rotation, and then you got to integrate it, and after you got this equation, you may rewrite this equation to be the form of this is going to be equal to integration of the moment due to the unit load time the real slope of the frame, okay, and then we arrive at this equation that can be used to determine the vertical displacement at what? At C, okay, and then if you prefer to find the horizontal displacement, okay, you do again, but this time you're gonna put the force at the point of C again, but this time the unit load gonna be in the direction of V sub CH, okay, it's going to be 1.2, and I should take a note that take a note, okay, elastic curve drafting the preliminary elastic curve, okay, will help us to specify the unit load. Okay, just take a note on this. This is important. This is important. Okay. And also, what we have next is, oh, let me have it. Usually, this is supposed to have the reaction here. And this reaction also produce related to the constant there. We have this one for a sub x, this one for a sub y, this one for m sub a. Just put it to exemplify the compatibility condition. Okay, next, what we have is this one. What we have is this going to be what? This is going to be 1 point. Okay, unit load, and this unit load gonna time this deformation. So the next equation we have 1.0 and time the horizontal displacement at C. Okay, that is going to be equal to the integration of what? This is going to produce m sub h. Okay, this is going to be the m sub h. M sub h is due to the point load. Okay, so you may put this one for the m sub h. And then again, it's going to time the real slope. That is going to be m dx over ei. Okay, and the last one, we are looking for the slope. So we're going to put what this time? We're gonna put the moment to our frame. Okay, and then this moment gonna be what? Gonna be in the same direction of theta sub c. So to determine this, we put this one as c of 1 point go in the same direction. If you put it in opposite direction, you will get the negative result. So don't worry about it. Everything gonna taken care by itself. So this one gonna produce m sub theta, and what we have is gonna be 1.0. 1.0 here, gonna time theta sub c. Gonna time theta sub c. And then it's gonna be equal to, this is external virtual integration of this one, m sub theta. And time the slope is gonna be m dx over ei. Okay, that is the first step. That's we setting up the concept of method of virtual work or unit load method to the problem we have. So the next step is we're going to determine. We're gonna do to determine what? Determine the m, because we going to use a lot of bending moment due to the applied force, and also we got to determine the m sub v to put it here. Okay, and then we got to put what? M sub h to get it here, and the last one we're going to determine m sub theta here to put it here. So next step, we're going to determine the moment equation of m sub v, m sub h, and m sub theta. You can go it step by step, right? But before we determine the moment equation, we going to set the coordinate of the frame. Okay, frame frame segment. Okay, segment of what? Of BC BC as x1 and AB as x2. So this is up to you. There is many choice that you can setting up the coordinate. Okay, some may set this is gonna be x1 and this is gonna be x2. Okay, but some people said I prefer to set this one as the x1 and setting this one as the x2. It's up to your choice, but you got to determine the best choice. Okay, if you use this x1, that means you got to determine the reaction at S, so it won't be convenient. Okay, I prefer to select this x1 and x2 better than this x1 and x2. Okay, so it's up to you. Everybody have their own choice. By doing that, let me cut this section. Okay, and then draw the free body diagram of the frame, and then we determine the equation of that. So this is going to be the first portion of that, and I'm going to put this one also in the frame. Okay, and what we have is the frame is subjected to the external load. This one is going to be the 10 kilonewton, and this one also subjected 10 kilonewton. You got the free body diagram here, and this is going to be the 10 kilonewton per meter, 10 kilonewton per meter. And what else do we have? You have the x1 here, and you have the x2 here. And then you can determine the moment, and you got to set the rotation of the moment. Okay, and following the sign convention. What the sign convention? The sign convention that we have is for the beam, and for the moment it's going to be like this on the left and like this on the right, and the shear is downward here and upward here. This sign convention we use is many times in the engine static. So I put this one as the M1, and if you like to put the shear, you may put the shear here also. Okay, and also by the same direction, let me put this one, okay, as the M2. This one may be as the M2, and then I set it for summation of moment equal to 0, and take moment here. The M1 will rotate in the same direction as 10 times x2, so the M1 gonna be equal to minus 10 times, sorry, x1, 10 times x1, and this is going to be our first equation for the M. And then if you prefer, you may take the moment here. We have the shear here also. Okay, summation of the moment equal to 0. Take the moment here. What we have is, this is going to be the resultant force. That is going to be 10 times x2, and it's going to be have the distance x2 divided by 2 here, and we're going to have the M2. This is M2 in this direction. This one also go by the same direction, plus 10x2, and it's going to have x2 divided by 2. And then if you take this, you have also this 2 meter gonna time 10 kilonewton. So you plus what? Plus 10 times 2 and equal to 0. So by doing that, you got this for 20. This is gonna be equal to minus 20. And also this one is a 5 minus 5, and then x2 square. This is going to be the next equation for capital M, the moment due to the applied forces. Okay, and if you like, you may draw this as the table as we have it before. Just put them into the table. For the table, what we can select is the segment. We have the segment. We have two segments here, right? It's going to be the BC and the AB. So just put this one as the BC and another one as the AB. And you may recall the X1, that is BC, gonna be from C to B, from 0 to 2. And for the X2 is going to be from B to A, that is from 0 to 3. And then the length of this. Okay, it's going to be 0 to 2 for X1 and 0 to 3 for the X2. And then you have the equation for the moment. That is going to be minus 10 x1 and then minus 20 minus 5x2 square. And this is going to have kilonewton meter. Okay, if you like to do so, and you may put this one in the green as you get to highlight it, and you don't miss it later. And then what we have is the m sub v. That is the m sub v, m sub h, the m sub h. And the last one is m sub theta. That is m sub theta, and that's what you have it over here, here and here. Okay, that is going to be the table that's going to help you during your putting the required moment to the virtual work equations. Okay, next we come to virtual equation. We come to this one, and again, when you put x1 here, x2 here, you gonna put the same here. This one gonna be x1, this one gonna be x2, this is x2, this is gonna be x1. You got to put all of that, okay, into your beam. So let's put this one into your beam, and this is going to be the, okay, and this is going to be the x1, and this is going to be the x1 also, and down here is going to be the x2, and here also is going to be the x2, and then your frame A, B, C, and your frame is A, B, C, and your frame is going to be A, B, and C. And now you are ready. Okay, when you cut this one, just cut this. So we have this one for the cut. This is going to be the C, and you also have this for 2 meters because your scale is 1 centimeter per 1 meter. So this is going to be 2 meters. So this is 2 meters. And then you're going to have this one for the x2. And all of them, you're going to have it just project it down here. Project this down here, and you may project this one down here also. You're going to have this one, okay, and you are also going to have this one, as you may have for all of them. So you need to follow what you set for the coordinate and also the direction of the moment, all of them must be compatible for each other. Okay, that means you're going to get what we said. So this one is going to be x1. This one going to be x2. And what we have is the first one, m sub v. Okay, that is going to be the next step. And you have this one for what? For m sub v1. And actually, if you find the sign convention, you got to capture here. So you got the summation of moment equal to 0. Over here, you have 1.0, okay, kilonewton per se. If you like to prefer to set this one kilonewton, and this one gonna be kilonewton meter to separate between the load of force and the load of moment. Okay, make it clearer if you like. And now, if you summation of moment over there is 0, what you have is m sub v1 gonna be, this is going to rotate, okay, about this point in the same direction. So it's gonna be minus 1. It's going to be minus 1 times x1, so minus x1. And then you come over here. Okay, and this time this frame is 2 meters, and the moment arm gonna be from here to here, and the m sub v2 summation of moment equal to 0. M sub v2 gonna be equal to, this time is minus of what? Minus 1 times 2, minus 2. Okay, so that is the first set that we get. The one is going to be minus x1, and another one going to be minus 2, and let it go by the yellow. Okay, let's go by the yellow. And next we come to this one, and at our point C we have the 1.0 here, 1.0 here, and what we have is the m sub h. So the same direction that we used before. So this one gonna be in the moment m sub h1, and there is no moment. Okay, so m sub h1 is going to be 0. You just put its summation of moment equal to 0. So this one is 0. And for this one is going to be x1, and this one is going to be x2. And what happened is, this direction we will follow it. Okay, and this one, what? This one has the one here, and if you the summation of moment equal to 0, what we have is going to be in the same direction, right? So the m sub h2 is going to be minus x2. Okay, it's going to same direction, and you put across in the opposite of equal sign, and then you get this. So next you get the m sub h1 0. M sub h2 is minus x2, and now you got this for 0 here, and this one for minus x2, and you get that second one. Okay, that's require a lot of consideration, right? You do a lot of practice in the past in static, so you can do so. And next one, this is going to be the x2, and this is going to be the x1. Now, the point C is subjected to 1. This 1 kilonewton meter, and this one also 1 kilonewton meter. And again, you use the same sign convention. So this is going to be the m sub theta 1. And summation of moment equal to 0. You take the moment here, this is going to rotate in the same direction. So this m sub theta 1 is going to be minus 1. Okay, and when you take it here also go by the same direction, and what you have is going to take summation of moment equal to 0, text over here, okay, and then what we have is m sub theta 2 have the same direction equal to minus 1. So we have, or we need to, okay, for the theta, and this is going to be, put this minus 1, this is going to be minus 1. That is the end of step 2. Determine the moment equations of this one, and this one, and put in your table. Next, we are going to go to the step 3. On the step 3, we determine phi sub phi c, v sub phi h, and theta sub c by using the virtual work equation, by using the virtual work equation. Okay, and it's going to require us do a lot of integration because the equation involved with the integration. So the first one, we put the green and the yellow, and then we gonna integrate it. And you should observe that the problem said the beam have different fractional rigidity. Okay, this one is 2i, sorry, this is 2ei, this one only 1 ei. So you got to notice this 2ei, this ei, and this is 2ei. Okay, if you integrate for the BC, you use this. If you integrate for the AB, you use this. Must be beware of that. Next, let me compute V sub CV. V sub CV gonna be equal to the integration of 0 to 2, and this one times this one, and then it's gonna times minus x1, and then it's going to be the x1, this time divided by only ei. Right. And then you got to integrate it, next one, 0 to 3, but this time you got for minus 20 minus 5x2 square, and now the x2, and don't forget this one going to divided by 2ei. That's it for the column. Okay, and then further integration, this is going to be 10x1 square. So you do the integration, you get 10x1 cube divided by 3ei, and then you get this integration from 0 to 2. Okay, oh sorry, this missed something. This is going to be minus 2. You got to time this with this. Okay, so this is going to be plus 40 minus 2, this plus 10 x2 square. Okay, and then you got to integrate 40 first, so plus, okay, 40 and x1, and now you got to divide it by 2ei, and then you integrate it from what, from 0 to 3, and last one plus, this time is 10, right? so it's going to be 10, and then x2 you're going to get it for cube divided by 3, and then it's going to have 2ei here, and you integrate this one from 0 to 3. Okay, you have the total of 3 terms, and then this is going to be equal to, like, the first one is 2 power 3 is 8t divided by 3, so this is 8t divided by 3ei. The next one is going to be 120, okay, and then 120 divided by 2, that is going to be plus 60 divided by ei. And the last one is this one. Cut this one into 5. This one is 27 times 5 divided by 3 plus 135 divided by 3 ei. Okay, if you may put into your calculator, this is gonna be 395 divided by 3, 395 divided by 3. It's going to be 131.67. This is going to be 131.67 divided by ei, and this is going to be downward. Follow the direction of the unit load. Here you got the positive, so that's going to indicate the direction of this. And if you prefer, you may put this one to compute by the ei, and then you got this one for 131.67, and then you divide it by ei. The E is 200 gigapascal, that is 210. Actually it's 10 power 9 and then 10 power 6 because we have kilonewton in our calculation. Okay, and then kilonewton per square meter. And the I, we have 110 power 6 millimeter power 4, that is 100, and 10 power 6 millimeter power 4 is 10 power 6 meter power 4. And if you push everything, it's going to be cut, okay, and it's going to be divided by 2, so it's going to be 6.58. 10 minus 3 meter. Okay, also it can be 6.58 millimeter and down. That is the first one. That's it. This is gonna be 6.58 millimeter downward. And then you do next calculation. This is for the first one, okay, and a lot of integration, so mathematics is important. Some students may have advantage on the calculator. I recommend you guys to buy the Casio like FX 9000 series, 8000 series, or Algebra series. You're going to use it in your future, not just today, and let's have it early, and it will help you to have time to get used to visit. Okay, next we're gonna take the second of this. Okay, this equation between the green and the orange to determine the horizontal displacement of C. Okay, that is going to be equal to And then it's going to be the first thing as before, integration from 0 to 2. And this one is going to be the same thing, minus 10x1 and time 0 dx1 over ei. Okay, this one gone. Okay, it's going to be 0. And then you're going to plus this. You're going to plus this one by the integration, but this time is from 0 to 3. From the 0 to 3. From the 0 to 3 of what of this? That is going to be minus 20 minus 5x2 square, and this one going to be minus x2, and now it's going to be dx2 over this time over the same thing over here over 2ei. And now what we have, minus and minus, this is going to produce 20 x2, and also minus minus plus, this is 5x2 cube. And now if you do the integration of this, you get the first term of 20 x2 power 2 divided by 2, and don't forget about this one, 2ei, and you integrate it from 0 to 3. And then next, this is going to be plus 5, and this is going to be x2 power 4 divided by 4. Okay, and don't forget about 2ei, and that's integration from 0 to 3. And now you may have this one cut into 5, so you have 5 times 3 power 2, that is going to be 9. 9 times 5 is going to be 45. So the first one you may get it for 45 over ei, and plus what? Plus this time is 5 and 3 power 4 divided by this. This is going to be 5 over 4 and 3 power 4. 3 power 4. 3 times 3 times 3. 27. 27 times 3. You may get it for 81. And then divided by this is 2ei, that is to be 8. Okay, and then ei. Okay, you got to reduce this. After you reduce this, you may get it for this is 765 divided by 8. $95.625. This is going to be 95.625 divided by ei, and then you get it in this direction. Okay, and if you prefer to do the calculation, this is going to be 95.625 and then divided by same thing, 200 and this is 100, so it cut. Okay, and then you got this 4.78 10 minus 3 meter, or you also can get it for 4.78 millimeter, and the direction is going to be in this direction. Okay, now this one we have this one of 4.78 millimeter. Okay, And next, zeta sub c. Do the same thing at the zeta sub c. At the zeta sub c, if you like. Okay, this is the end of this one. Let me have the zeta sub c. Zeta sub c is equal to the same thing. This one gonna be this one and this one. Okay, and then it's gonna be integration from 0 to 2. This time it's gonna be this one and this one. Minus 10x 1 time minus 1 time minus 1, and then you have this one for dx1 over ei, and then you plus it for the second one, integration from 0 to 3, and this time you have minus 20 minus 5x2 square, and then again you time minus 1, and now you have this for dx2, and then divided by 2ei. Okay, and now this is what? This is gonna be 10x1, and you can do integration of that easily. This one gonna be 20 plus 5x2 square. By follow that, you will get the first term of what? Of 10x1 square divided by 2, and then ei. You do the integration from 0 to 2. Okay, and then next this one plus this one is 20. Okay, you can get it for 20 and time x2, plus this time you're going to divide it by 2ei, and you integrate from 0 to 3, and the last one plus 5x squared 5x2 power 3 divided by 3, and also 2ei, and then you do the integration from 0 to 3. Okay, and then what we have is this is cut. This is going to be 5 times 4 is going to be equal to 20 over ei, and this is cut, this is 10, and you're going to have 3 times 10 plus 30 over ei, and the last one 5 times 3 power 3, 5 times 27, okay, and then divided by 6, and then you may get this one divided by ei, and finally you may get this one for 72.5. So this one gonna be equal to 72.5 divided by ei, and have the rotation in this direction. And if you like to determine the value of it, it's going to be 72.5 divided by, again, 200 and times 100, and then you get this one equal to 3.625, and 10 minus 3 radian. It must be in radian. Okay, it must be in radian. So that is what we have for this, and if you prefer, you may use what you determine and to push all of them onto the scale. Okay, And if you do this, just make this thing like 4. Okay, 1, 2, 3, 4. Okay, 1 meter, 2 meter, this is 4. And this is going to be 6. Okay, that is going to be 1, 2, and 3 meter. And you may have this for this is fixed at A, B, and C, and is subjected to the required force, and also this 10 kilonewton, 10 kilonewton. Okay. Oh, actually it didn't matter, but it's important to put this one at 10 kilonewton here also. Okay, what we have is 6.58, 6.58, about 6.6. Okay, if you make it 2 times, it's gonna be about 6.6 is 6.5. About this. Okay, it's gonna be downward here. Okay, this is gonna be 6.6, 12.4, about that. Okay, and this is about 4.8. 4.8 is about 9.6 millimeter, about this. So what we have, this is V sub C vertical equal to 6.58 millimeter. This one is what? This one is V sub C H, and it's going to be 4.78 millimeter. And over here, you're going to have the clockwise for 3.625. So this is going to be some kind of 3.625 10 minus 3 radian. Okay, and since this one is moved for 4.75, about 9 millimeter, and you may see this one is going to be about here. This is going to be V sub BH equal to 4.78 millimeter, since the beam, okay, has no axial deformation. Since it's have the same, so it's going to be like that. It's going to be equal to that. Okay, and then what we have is this is going to be the fixed end. This is one move. So when you put this like here, and it's going to arrive here, that is going to be B palm, so it's going to be have the deflection like this. This is going to have what? As you may know, the V sub A H, V sub A V, and 0 sub A all 0. And over here you also have V sub B V equal to 0 if you like to check. Okay, and the last one, this one must taking care of their perpendicular. Okay, even though it's alive here, this must be keep itself as the normal angle. Okay, and this portion of the beam will deflect like this. And when it's alive here, that is going to be C palm. This is going to be B palm. This is going to be the elastic curve, okay, of this beam. Elastic curve of this beam. And if you prefer, you have the equation of the deformation, right? You also may be able to draw the moment diagram of this beam. 1, 2, 3, and 4, if you like. And you prefer, you may put this a little bit here. Okay, and then what you have for the equation? The first one, 10x1. So if this is x1 start here, this is going to be 0. And for 1 meter here, that is minus 10. So it's going to be like minus 10. Minus 10 here. For 2, it's going to be minus 20. It's going to be linear. And this is going to be minus 20. And then for x, we start from here. If x 0, it's going to be minus 20. Minus 20. And if you prefer, go by 1 meter, 2 meter, and 3 meter, follow this. For 1 meter, that is going to be minus 20, minus 5, minus 25. 10, 20. This one. Minus 25. If it's 2, it's going to be 5 times 2 square. That is 40. That is minus 20 and minus 20, minus 40. 1, 2, 3, 4. Minus 40. And if it's 3, that is going to be 9 times 5, 45. And then it's going to be 65. 20, 40, 60, and then about this, that's this, minus 65. So you can draw the moment diagram of this frame like this. And it's going to be, see, follow this. Since this is negative moment, okay, this is also the negative moment. When it's negative moment, the curve going to be like this. And it's going to be like this. So it's corresponding to our curve here and our curve here. Okay. And the last thing, if you prefer, you may draw the reinforcement. This is the M diagram. If you like, just put this 1, 2, 3, and 4. And then you may put this 1, 1, 2, 3, 4, 5, 6. And what we have, if this one is the reinforced concrete beam, you also can use the moment diagram and elastic curve to find the pattern of the reinforcement. Usually we have reinforcement like this for the beam, but for the frame. But when the subjected to moment like this, we always put the reinforcement on the tension portion. So extra reinforcement must be put, in this direction, and also in this portion of the beam. So this is the reinforcement, the reinforcement pattern. Okay, and that's all we can do for this problem. We can draw the elastic curve, we can draw the moment diagram, or even we can put the reinforcement pattern that's corresponding to our moment diagram and our elastic curve. This frame as shown, they says is going to be the still rigid frame. What is mean by still rigid frame? Still rigid frame, when it says rigid frame, most of rigid frame must have what's so called the rigid joint. This frame have rigid joint at the B, and it has the roller. This one is roller at A, and it has the pin support at B. And it said all the beam have the constant stiffness. What so called is this beam have the stiffness of EI, and this one also have the stiffness of EI. When we talking about stiffness of the frame, okay, what's the E? E is going to be the modulus of elasticity, and the I is going to be the moment of inertia. So the fractional stiffness of the frame composed of one for the material, another one for the cross section of the member of the frame. Okay, as we have under the application of the force, they ask us to determine the horizontal displacement at A and the slope at B. When you solving the problem of deformation of structure, it's a better times for you to consider how the structure respond to the applied forces. When you consider the response, you're going to consider the support also. If it said this is the pin, what is mean by the pin? The mean by the pin is the deformation over here at point C in the horizontal direction, and the deformation or displacement of point C in the vertical direction is going to be 0. The pin won't allow this to displacement, because the pin gonna have the reaction here, the A sub y, that's going to prevent the displacement in the vertical direction, and it also has the A sub x to prevent the movement or the displacement in the horizontal direction. Okay, and what next? The pin will allow the member gonna rotate. Okay, it can allow rotation. So what we have is they're gonna have the theta sub c gonna be any value, and then the application of point B gonna move the beam together. Okay, since the deformation is the beam is very small, that means if this one move like this by this amount, for example, you draw it by the neutral axis line of the member. So let's say this is 1 centimeter. This one gonna move by another 1 centimeter. Okay. You may say due to very small, okay, very small deformation along the what's the AB axis. We have this is delta V horizontal, and this is gonna be delta B horizontal. So we have delta A horizontal equal to the displacement SB in the horizontal, and what we have is going to be equal. Okay, by rigid joints, what this means is if this one is 90 degree, so after deformation, this point must also be 90 degree. Okay, it's gonna have the same perpendicular angle. And what we have is, so this is gonna move from here to here, and the same time this one also need to go to here, because over here delta V in vertical is 0. There is no vertical movement. Okay, we are going to determine delta V in the H direction and also theta A. Okay, we don't know the theta A yet. And by this movement, the deflection of the segment AB gonna be in the form like this. Should be in the form like this to have the continuous deformation. And what we have here is what this is gonna be theta sub B. Okay. And how about the vertical movement here? Okay, due to the small deflection along the AB axis, we have this equal to 0. The same thing, due to the small deformation or shortening of the column BC, the V sub B in the vertical direction gonna be 0. So what we have, we know this guy is 0. Okay, we know this one is 0 because it's respond to the condition of the support. Okay, and also we know this is 0 due to what? Due to very small deformation of the, let's say, of the BC and AB, BC and AB. Okay, so we have first condition for the BC, we have a phi at B vertical equal to 0, and phi at A horizontal and B horizontal equal. That is going to be respectively. Okay, and what else do we have? By considering this, we have this horizontal movement. They are equal, but we don't know yet. Okay, we will determine the horizontal displacement at A, and if we know this also. And also they ask us to determine the slope at B. Okay, and if you prefer, you may go to determine the slope at C. So at C is going to be, this is along the axis of the column. This is going to be theta sub C. Okay, and also over here, you may determine what's so-called the theta sub A. This is going to be the theta sub A. So we can group what we understand for the elastic curve. Okay, some you may know, some you got to determine it. And now they ask us to determine the slope at B and the horizontal displacement at A. Okay, after you trying to understand this structure, okay, you got to go back and take a look at the principle of virtual work. From the principle of virtual work, we have the virtual work equation. What is the virtual work equation? The virtual work equation said the external virtual work of the structure is going to be equal to the internal virtual work. That means what act outside is going to be equal to what act inside. Okay, and by doing this, let me put the explanation by drawing some more structure. Let's say let me have this one for the frame of 3 meters. So let me set 1 centimeter is equal to 1 meter. So 3 meters is going to be 3 centimeters. Let me have this one, see 3 centimeters, and this one also 3 centimeter. And what they ask us to determine, they ask us to determine the horizontal displacement at A. By the virtual work, you got to put a virtual force. Okay, if you determine the displacement, you put the virtual force of 1.0 unit to the structure. And then imagine the multiplication of this 1.0 force and this real displacement. This real displacement is kind of external displacement. So 1.0 that's time the vertical, sorry, so time the displacement at A in the horizontal direction. This is the real time, this is assumed, so it's going to be virtual work. And since it is due to the displacement, it's going to be the external virtual work. Okay, and this is going to be equal to, okay, due to the deformation, this is due to the moment that causes by the given applied force. Okay, and then your structure gonna deform. The deformation of this structure is by what? Is by the elastic beam theory. D square V by dx square is equal to m over EI. Or you may recall this called the curvature of the beam, curvature, C-U-R-V-A-T-U-R-E. And you also have what? You can also have the slope. Okay, the slope is dv by dx is equal to theta. By doing this, you may draw this one, d by dx. And by mathematics, okay, you may say this is going to be dv by dx, and it's going to be equal to m over ei. And this is what? This is theta. So your equation is going to be d theta by dx equal to m over ei. Or you may say this is going to be d theta equal to m over ei and then dx. Okay, this is going to tell us the change of the slope along the curve, okay, is equal to moment divided by fractional stiffness times the small element dx. Okay, now this structure, when it's subjected to the horizontal force at A, this is going to produce the bending moment m sub h. Okay, this assumed force produce this assumed displacement. Produce this assumed moment when it time with the slope here. Okay, you know the force. The force has to sink the work by the force is the force time displacement, linear displacement, or also this is linear displacement, okay, this linear displacement, force time linear displacement, or work may be equal to moment. This is going to be moment time what? Time rotation or time slope. Rotation or slope is the same thing. So this is the moment. It's going to have the deformation here. So we have m sub h d theta, and since it's going to be along the whole length, so over here you got to integrate it. Okay, if you get a little bit further, you may get this one gonna equal to integration of m sub h, and then now you put this over there, it's going to be m over ei. This is going to be m over ei and then time dx. This is going to be the virtual work, okay, equation to determine the horizontal displacement at A. And now, if you guys have another one, let's say if you have let me have this one here, another frame to determine the slope at B. To determine the slope at B, what should we have? Is the same frame, but this time thing is changed. You are interested in what slope at B. Okay, this is slope at B. That's slope at B. What happened is, by the principle of virtual work, you gonna put the virtual moment at B. So you got to put virtual moment 1.0, let's say kilonewton meter. This is kilonewton to differentiate them between the shear and the moment. Okay, and what we have is very similar to here. This time the 1.0, and then it's gonna time what? It's gonna time the slope at B. It's gonna time the zeta sub B. Okay, and this one gonna produce m sub zeta. It's different from this one. This one is m sub h due to the 1 unit load at A. This is m sub zeta due to the moment, assumed moment at B. And that is going to be equal to integration of m zeta and time the change, the differentiation of the slope here, time the d zeta. Okay, and then if you do the further, this is integration of m sub zeta and time what? Time m over ei, and then d zeta. Okay, that's the equation. Oh, dx, sorry. Okay, that's what we have is the first step of our consideration. Actually, we do consider how the structure respond to the force, and we have the draft elastic curve with the displacement and slope as important point. Some may known, some may not. Okay, and then we come to the principle of virtual work. We have the virtual works equation. Okay, this time we have two of them. One to determine the horizontal displacement at A. Okay, for this equation, that means we got to put 1.0 at A, and that's going to produce the moment m sub h. 1.0 time this one is external virtual work, and m sub h time the d zeta according to the structure, that's going to be the internal virtual work. To determine the slope at B, just put assume unit moment at B, and this assumed unit moment time the real slope, that's going to be the external virtual work, which is going to be the assumed bending moment. Okay, and time the real deformation of the structure. And the next that we are going to determine is going to determine what is the moment. Okay, so we going to find the moment equation. We going to find the moment equation, which is going to be m here, and m sub h here, and the last one, and m sub zeta. Okay, if you like to determine the m here due to applied force. Okay, we're going to start by taking the structure and determine the reaction and then after the determinate reaction you can find the equation of moment. Anyway, before you can find the equation of the moment, you got to specify the coordinate. Okay, to taking care of this, you may have choices. It's up to you to taking care. Some of the people may say, okay, I put this one as the x1. Okay, and that's x2. This one for the x1. Okay, and I may like to put this one as the x1 and this one as the x2. It's up to you. Okay, yeah, you can select anything you like, but the best way is trying to define the coordinate with appropriate, okay, with appropriate or proper manner. If you select kind of this one, it's going to be very hard to determine the moment equation, okay, compared to the what I proposed by the blue color here. Okay, for myself, I'm going to use what I'm proposed here, and if you like, it's up to you how you're going to select the coordinate, but the best one is better. Let me take this one as the frame again. Okay, by doing this, under the application of the force, what we have is what 4 kilonewton per meter. Okay, we have the uniform load here, and you also have 20 kilonewton. So this is the force of 20 kilonewton. This is 4 kilonewton per meter. Under the action of the force, what happened? This is gonna be A, this is gonna be B, this is C. If you mark here, you may see the force gonna rotate your structure in the clockwise direction. So surely A sub y must be in this vertical direction. Okay, and the same thing, the horizontal force act at B from the left to the right. So I believe the C sub x should be here, and due to a lot of applied force in the vertical direction, so this one also should have the C sub y here. And now you are ready to determine the reaction occur on this frame. Okay, and you may start by summation of what? Of the f sub x equal to 0, and then you may see the c sub x, put this one is positive, so your c sub x over here is going to be equal to 20 kilonewton. That is going to be very easy. That is going to be equal to 20 kilonewton. And if you prefer, you may summation of the moment about C, this one, about C equal to 0. If you take moment about C, the A sub y gonna have the moment arm of 3 meter. So you have 3 A sub y. And then the rotation here gonna be positive. Here is gonna be positive. And what we have is going to be the force, resultant force here. That is going to be 4 times 3. The 4 times 3 going to be what? The 4 times 3 going to be rotate in this direction. Okay, that is going to be what? That is 12 times 1.5. So it's going to be equal to 12 times 1.5. And you also have the 20 kilonewton times t in this opposite direction. So plus 20 times 3. Okay, and if you put them together, you may get the A sub y equal to 26 kilonewton. So this is 26 kilonewton, and the line here to mark it more clearer. Okay, and then this is gonna be 26 kilonewton. And if you do the summation of f sub y equal to 0 now, c sub y is upward. So this is upward, is positive. C sub y plus 26. Okay, 26. And what we have is going to be C sub y plus 6 equal to 4 times t is 12. So your C sub y is going to be 12 minus 26 is going to be minus 14 kilonewton. So the real thing that C sub y is going to be in the opposite direction here. Okay, now we are going to determine the moment equation M. Okay, let me put this one into the pink. Okay, we are going to determine this one. So we're going to cut this one. When you specify all this coordinate, you got to follow them, follow what you assign to at x1 and x2 all the frame. Okay, while doing this, you may cut this one, and then since you didn't have much area here, let me put this portion of x1 here. Let me put this one here. Put this one in this location. Okay, it's not that hard. Just put this one here, and you have c sub x of 20 kilonewton. Okay, and also you have the c sub y in the opposite direction there, so this one going to be downward of 14 kilonewton, and the coordinate you are using here is going to be the x1. Okay, and for this one you cut here, this is going to be x2. Okay, this is going to be x2, and let's put the x2 here. This one going to be the a, and then you have this one for the a sub y of 26 kilonewton. So this is going to be 26 kilonewton, and the uniformly distributed load is here, and this is going to be the x2. Okay, now you have the free body diagram of this portion x1 and this portion for x2. What we have is we are going to use the sign convention, for the moment that we have in the static. Okay, if this one, you may have the chair here also. Let's say this one going to be the M1. Okay, M1. And if you take the moment here, you may set if the summation of the moment equal to 0 about here. So your M1 is going to be what? Your M1 is going to rotate this one. 20 times x1 going to be in the opposite direction. So your M1 is going to be equal to what? Equal to 20. And then time x1. That is the first one. Okay, and if you prefer, this is coding the blue, right? So you put the blue here. And then the other one is here. Following the sign convention we have for in static, the moment here is going to be capital M2. Okay, and what we have is going to have the moment here, and if you prefer, you may take summation of the moment. Here is 0. Okay, and then this rotation is positive, so you have this one for M2. Okay, M2 is going to be equal to this 26 times x2. That is going to be 26 times x2. And you also have this one for what? for 4 times x2. This one going to be 4 times x2. And it's going to be the distance here of x2 divided by 2. And it's going to be in the same direction of m2. So we put across the equal sign. This is going to be 4x2. And then it's going to times this x2 by 2. Now, your m2 is going to be equal to 26x2. And this is cut minus 2x2 square. Okay. We have this capital M2 for our capital M. And the x1 going to be from 0 to 3. And x2 also from the 0 to 3. Okay, from A to B to 3. And then we come to this one. And if you prefer, you may put the structure here, and you may draw the free body diagram of them. And let me just put the reaction here. This is going to be the A sub y. Okay, and this is going to be have the vertical direction, because the one gonna have the moment here, and it's gonna rotate this way. But this one gonna rotate upward. Okay, and that's you mean you can take that A sub y easily. The 1.0 gonna have the reaction here. That is gonna be the C sub x, and due to the A sub y here, you're going to get the C sub y here. Okay, by doing this, we take summation of the moment about C equal to 0. If you take this, the C sub x and C sub y gone, you have the A sub y. The A sub y gonna time by this distance 3 meters. So we have 3 times A sub y. That is going to be the moment here. And one is going to time this distance. Okay, the moment arm here. So equal to 1 times this distance of 3 meters times 3. Okay, by doing this, you get A sub y equal to 1.0. Okay, that's quite easy, right? Okay, that's quite easy. Summation of x sub x equal to 0. You may have C sub x. This one is positive. And then you have the C sub x equal to 1. And finally, if you do the summation of f sub y equal to 0, downward is positive. So C sub y equal to upward, up to 1 also. So we have A sub y equal to 1. C sub x equal to 1. And C sub y equal to 1. Okay. If you prefer, you may push this one for the yellow. And then you get the reaction already. Now, it's time for you to cut the structure, right? Okay, just cut it. And for this one, you may cut it along this line here. And this is going to be point A, and this is going to be 1.0. And A sub y here is going to be 1.0. And the reference here is x2. So this is x2. You get this, right? And the next is here. If you like, you may just put this portion into like this. Just put it here. Cut about here. Actually, it should be here, but we don't have the area around here. If you put here, okay, if you like, you may put it over here. And then you have this one for 1.0. C sub x. You also have this one for 1.0. Okay, by doing this, you may take the moment by the same direction as before. This one is here, so this one is gonna be m sub h. Okay, m sub h, m sub h. This is x1, right? M sub h1. And this is gonna be the m sub h2. Okay. Now, you may start by taking this. You may taking the moment here, summation of the moment here equal to 0. What we have is 1.0 here produce no moment. But this one gonna have the moment that's in opposite direction to m sub h1. So we have m sub h1. Okay, that is gonna be equal to m sub h1 is equal to x1 equal to the 1 and then time x1, and again the same thing, summation of the moment equal to 0 here. You have this one here and this one produce no moment. This 1 unit gonna time x2, so this is m sub h2, m sub h2 equal to the 1, and then time this is going to be x2. That is the result of this calculation. This one and this one. And the last one is here. You do the same thing. You just said this is going to be what? Take a moment here. This is clockwise. So the force here supposed to be upward of a sub y. Okay, and since this is upward, there is no force. So this is going to be c sub y downward. And how about the horizontal force? There is no horizontal force. So this is c sub x. Summation of x sub x equal to 0. C sub x is 0. Okay, and if you take summation of moment about c is 0, this time a sub y is like this, is positive. This one also, this is positive. And then you have what? You have a sub y times this distance of what? Of 3 meters. So you have 3 times a sub y. And this is going to be counterclockwise moment. That's equal to 1. Okay. So your a sub y is going to be 1 divided by 3. That is going to be the result of this. And the next one, summation of x sub y equal to 0. You may see that the c sub y going to be what? This is downward. Downward is positive. And this is what? Going to be 1/3. Okay, you got this, you got this, and then you got this for the result, for the reaction. And then again, this is going to be the x1. And this is going to be the x2. You may do the cutting the same as before. This one. You may do the projection from here up down here, and you have this one for 1/3, and this one gonna be the x1, and your moment here gonna be the m sub. Oh, this is x2. This x2. This m sub theta 2. Okay, this is the x2. For the x1, you cut this here. Okay, you cut the element here. You have the c sub y equal to 1/3. So this is gonna be 1/3. And c sub x is 0, right? And then the moment by the same direction, that is going to be m sub theta 1. Now, if you do the same thing, you just take moment here. This is the shear also. Summation of the moment equal to 0. So this one is going to be positive. You may have what? This one passing to the point of taking moment. Okay, passing to this. There is no moment arm. So m sub theta 1 is going to be 0 here. And for this one, summation of the moment equal to 0. Take the moment here. So this is going to be easy. This is going to be 1/3 times x2. So m sub theta 2 going to be equal to x2 over 3. And then you have this one for m sub theta. And this is the result of our determination of the moment equation. We have the equation for capital M, m sub h, and m sub theta. And if you prefer, you may put all of them together in a form of table. Okay, let's say this is going to be the segment. What segment do we have? What segment do we have? We have the segment CB. Okay, CB. CB is for x1. So this is CB. And segment what? AB. AB. AB for the x2. Okay, and then we may put them into the table like this. And we have the length. Okay, the length 1 for the x1, the length 2 for the x2, that is going to be from 0 to 3. And this is from 0 until 3. And it's going to be in meter, like this. And next one, we have the equation of the moment m. We have the m. And we have the first one of this is going to be 20x1. 20x1. And if you like, you may draw like here also. And the other one, you have this one 26x2 and minus 2x2 square. Okay, that is very clear on this. And next one, we have m sub h, m sub h. And the last one, we have m sub theta. We put this one here and this one here. M sub h, what we have m sub h, this is m sub h1, we have is for x1. And this is m sub h2, m sub h2, and then we have it for x2. And the last one, m sub theta 1 is 0. And m sub theta 2 is going to be x2 divided by 3. Okay, that is going to be the conclusion. And our conclusion is kind of very nice and clean on this. Okay, and then they are going to ask us to determine what they ask us to do. For the third, we determine V horizontal displacement A, V sub A in horizontal direction, and theta sub B. Okay, we have all the required equation is here, so we can do it by follow that. The first one, delta AH, displacement at A in the horizontal direction is going to be integration of this one and this one. Okay, that is going to be about integration of this pink and yellow, and it's going to start from C to B. Okay, start from C to B. So integration of 0 to 3. The first one is 20x1 That is 20 x1, and it's gonna time x1. Okay, and this one gonna time dx1 divided by ei. Okay, they are equal ei. They have equal value of ei. And next, do the plus for next section is here. You integrate it again. Integrate it from 0 to 3. From 0 to 3. And we have the moment of this one, 26x2 minus 2x2 square. And then we time it by the x2. And it's going to be dx2 by ei. This is going to be dx2 by ei. And this one we have 20x1 square. This one we have 26x2 square minus 2x2 cube. Okay, by integrating this one, the first one, all of them have the same ei, right? So the 1 over ei can take out like this. Okay, the first portion is going to be 20x1 power 3 by 3, and then we're going to integrate it from 0 to 3. And the next one, this one is going to be plus, it's going to be 26x2. Okay, it's going to be x2. It's going to be x2 square is cubed divided by 3. And again, this one from 0 to 3. And minus 2. This is x2 power 4. And divided by 4. You integrate it from 0 to 3. Then you close this. Okay. And then if you prefer, you may go further, 1 over ei. And this one is going to be 3 power 3 divided by 2. So 3 power 2. That is going to be 180. So you get this one for 180. Okay. And then you're going to have the answer for the second one. You put this number, you got to have it for 234. 234. And then you have it for minus 40.5. Okay, and then if you put everything together, you may get the result of this of 373.5. This is 373.5 divided by ei. And since it's positive, okay, this is going to be in this direction. Okay, and then if you go further, now you get the V sub AH for 373.5, and it has this direction divided by ei. And coming into this question, they said if E is 200 gigapascal, that's for the steel. Okay, they asked the allowable horizontal displacement is 15 millimeter. They asked us to determine the moment of inertia. Okay, now from the equation that we have, okay, over here it says we're going to have the maximum of the horizontal displacement here of 0.015. Okay, that is meter, and they ask us to determine the I. So the I is going to be, you take the I up, so right here, it's going to be 323.5 divided by, takes the I up 0.015 and meter. Okay, and you have the E. We compute it in kilonewton, right? So our E is going to be 200 gigapascal is going to be 210 power 9 Newton per square meter. So this is going to be power 6 kilonewton per square meter. Now, by doing this, okay, you will get this one of 124.5. This one divided by this one divided by 200, you will get this. And this is 10 minus 6. And the unit is going to be in meter, so meter power 4. Okay, if you like to change it into millimeter, you just times it by 10 power 12. That is going to be 10 power 6 millimeter power 4. Okay, you may answer this into the appropriate area. That is 124.5 and 10 minus 6 meter power 4. Okay, that's it, first one. And then they ask us to determine the slope B. Okay, and put the EI into that equation. You will get the slope B in radian. Now we go further to determine the slope. Let's see what we have is here. The slope is going to be integration of this moment and this moment. Okay, we put it. This time is between the pink and the green. The pink and the green. And then we have all this is theta sub b. That's going to equal to integration of 0 to 3 for this one, 0 to 3, 20x1, 20x1, 20x1. Gonna times 0. Okay, that is gonna be 0 dx1 over EI over EI. And then plus another integration from 0 to 3. Integration from 0 to 3 of what? Of 26x2 minus 2x2 square, this portion. And then it's going to have x2 divided by 3. So this is going to be x2 divided by 3 and dx2 over EI. And now we have is 26 x2 square divided by 3 minus 2 x2 cube divided by 3. And if you do the integration, you may get this one for 1 over EI. And we have 26 x square, x2 square, x2 cube divided by 3. Okay, divided by 3. And then you have 3 already divided by 3. And then you have this 3 already, so it's going to be 3 here because it's going to divide it by 3 here, 3 here. And that is going to be from 0 to 3, right? So 3 to 3. And next we have minus 2, and if you like, divided by 3. This is going to be x2 power 4. 2 power 4. And you have 4 here. And now you integrate it from 0 to 3. Okay, and then you close this. After you put everything together, you may get this one for 264.5 divided by EI. And since it's positive, so that means it's gonna rotate like this, as you specify when you determine this one. Okay, it's going to be have the same direction as this one. So it's going to be 64.5 divided by EI. That is going to be 64.5 divided by EI. The direction is going to be from here to here. Okay, and next, if you put the EI into this equation, you will get this for equal to 64.5 divided by E. E is 210.6 kilonewton per square meter. And I is going to be here. Okay, 124.5 and 10 minus 6 meter power 4. So this one cut, this one cut. After putting into your calculator, this is gonna be 2.59 and 10 minus 3. The unit is radian. Okay, that is going to be the answer. 2.59 10 minus 3. This is 2.59 and 10 minus 3 radian with this rotation. And then they asked us to draw the moment diagram from the moment equation and draw the elastic curve. Okay, now we come over here. What we have is the equation of the moment. We have two of them. One for this column and another one from this beam. Okay, the equation is here and the equation is here. For this one is for the column. If x1 equal to 0, this one gonna be 0. It is a linear equation. If x1 equal to 3, that is going to be equal to plus 60. Let's say this is going to be plus 60 kilonewton meter. And you may have this one as the linear. This equation is not linear, okay? It's going to have the curve because it's the function of polynomial power 2. It's second order. And if you put this one as 0 here, this one is 0 here, this one gonna be 0. If you put this one for the 3, it's gonna be here. That is going to be 26 times 3 minus 2 times 9. You're going to get this one for 60. Okay, this one is going to be plus 60 kilonewton meter. Okay, and if you put something in between, okay, you may get about this. And you will have this one as a curve. Okay, this is the moment diagram that we can draw from the moment equation. What we have is, this is positive. And again, this is going to be positive like this. So the curve of the elastic curve we are going to have is will be corresponding to this. If you redraw it again, this is going to be the pin, right? So this will have only rotation of theta sub c, and you got this one for 373.5. Let's say this roller here is can move by this distance of 1 centimeter. This one also gonna be here. Okay, and you may have this distance is gonna be equal to this distance I explained to you already. This is gonna be delta. Oh, sorry, the displacement at what? At A in the horizontal direction. This is gonna be T23.5 divided by EI, and this is the horizontal displacement of B. Okay, is going to be equal to T23.5 divided by EI, because the deformation, axial deformation of the beam and the column is really small. Now, this B will rotate with 64 divided by EI. So this one gonna rotate like this. Okay, the light angle here is still keeping as before, and the rotation here, you know, this one is going to be 64.5 divided by EI. If this is 64.5 divided by EI in this direction, this one also 64.5 divided by EI. Due to what? Due to the rigid joist. Okay, and then this will also provide us with the slope, but this slope is unknown yet. If you like to determine it, you can find zeta sub c. And now the deformation of this column should be like this. And also, since this one is moved to here, okay, this portion gonna rotate this way, and you also may have this one as the unknown of the zeta sub a, okay, equal to what? And as you mentioned, we have what? We have displacement at C horizontal equal to displacement at C vertical. This is 0. And we have also displacement at A. This is A. Okay, that's A in the vertical direction is equal to 0. And we have the displacement at B in vertical direction equal to 0. Okay, you may see that each point gonna have three. This is 3 displacement. This is horizontal, vertical, and slope. Horizontal, vertical, and slope. Horizontal, vertical, and slope. Okay, that is going to be the elastic curve. And if you like, you may put the steel. If this one is not the steel, if it's built by using the reinforced concrete. Okay, if you build by using the reinforced concrete, you may also sketch how you put the main steel into your structure. Since most of the beam have their own reinforcement, most of them have their own reinforcement already. It's on the top and on the bottom. Okay, to make it easy to construct. But by putting this, what more reinforcement is supposed to be put in? Since this is intention, okay, see, we're going to put the steel in the tension portion of this one. So more reinforcement must be placed here to resist the tension due to the moment, and also here, okay, to resist the moment there. So this is going to be the reinforcement okay, pattern. Okay, if you like, you may draw this also. example, we going to analyze the steel rigid frame that's shown here. This frame has the support of pin at A and the roller at B. Under application of the force, this frame gonna deform, and they requires us to determine the displacement at B and also at C. This steel frame, it has two columns and one beam. All of them have the equal E and I. That means this frame gonna have a constant EI or a constant fractional rigidity. Okay, and we will use the EI to compute the magnitude of the horizontal displacement and at B and C later. Now, before we start, I think by the method of virtual work, the first step, we're going to consider the elastic curve of the frame and the virtual work equation. Virtual work equation. Under the application of 40 kilonewton, the pin would move. Okay, since the pin prevent the movement in the horizontal and the vertical, that means the displacement at A in the horizontal direction equal to the displacement at A in the vertical direction, and it's going to be 0. Okay, however, the rotation can occur here. Okay, the rotation here can occur. It's allow rotation for the pin. And under the application of 40 kilonewton, for sure, this point supposed to move to somewhere here. Okay, and due to this kind of movement and due to the moment that may occur in the column AC, this part of the frame should be curved like this, and we may have this as the zeta sub A. When the column AC curve like that, what happened is this is the rigid frame. So the joint C, when it's moved to C palm, okay, is going to maintain its perpendicular between the column and the beam. And let the displacement from C to C palm, let's we call it V sub C H. Okay, this is going to be the vertical direction. At this point, what we have is the rotation of the joint C in the beam and in the column. They are going to be equal. Let it be equal zeta sub C. How about the vertical, the displacement at C? Vertical displacement at C is 0 due to very small deformation of columns. Actually, the phi sub dv gonna be 0 because on the column is very small compared to the author displacement. Okay, and then we're going to have this also. And what happened is the D also gonna move in the same amount of C. So if this one is about 1 centimeter, this one supposed to be 1 centimeter. Why? Because the same thing. Because the beam V sub CH is going to be the displacement as DH due to very small deformation of the beam this is of the column, this is the beam CD. Okay, and then we have that. And if this occur, what going to be the rotation over here? Yes, over here they're going to have to bend from here to here. And what happened again? The angle at this point will be maintained at perpendicular angle. So this must be like this. And then the rotation here, and here, the rotation from here to here and from here to here gonna be theta sub d as the unknown. And since this B is the roller, so the displacement at B in the vertical direction gonna be 0. The roller have the reaction B sub y. Okay, so this displacement is 0, and it can move horizontally here, right? So this is going to be V sub B horizontal. And since the reaction at the B is only in the axis of the BD, so the BD have no moment. Let's say M sub BD gonna be 0. So this is gonna be straight line, and it's gonna have the displacement of the column BD like this. Okay, and what we have is this is the phi sub B horizontal. So based on what we have, we're going to determine this V sub B horizontal and this V sub C horizontal basis upon what they're asking us here. And then we have the virtual work equation. From the virtual work equation, what we have is the external virtual work must be equal to internal virtual work. What it means by this? If we like to use the method of virtual work, we're going to apply a unit load to determine the displacement in the horizontal direction. Okay, first one, they ask us to find at B. So by doing this, it means that we gonna apply the 1.0 force, very small force, into the frame that is in equilibrium. Okay, when this happen, is the V sub BH is the real displacement times the assumed 1.0 force. So this is gonna be work. Okay, the displacement time the unit force. So this is going to be the virtual force V sub BH, and this is gonna be equal to integration of what? This 1 unit force gonna produce the moment in every segment of the frame. Let's call it M sub BH. Okay. The M sub BH also gonna produce the virtual work when this time the deformation of the frame. The moment supposed to time the slope, okay, to produce the work. And what is going to be the change of slope of the frame? We have the elastic beam theory of d square v by dx square equal to m over ei. Okay, and based on the mathematics, this is gonna be d by dx of dv by dx, and it's going to equal to m over ei. Okay, and you may have this is as the d theta. The small change differential of theta is going to be equal to m over ei dx. And now, if you put that into this equation, this is going to be integration of m sub bh times what? Times m, okay, over ei dx. What is the m? The m gonna be the moment that's occur due to the applied force due to the 40 kilonewton. Okay, so assume force times the real displacement is the external virtual work. The assumed force produce the bending moment and time the real change in the shape of the frame is going to be the internal virtual work. And again, if we put the 1.0 unit force, this time we like to determine the horizontal displacement at C. So we go to the C and we put the 1.0 force there. This 1.0 force gonna time this real displacement. So what we have is going to be 1.0 time phi sub c h, and it's going to be integration of what? Of moment due to the 1 unit force. This is moment at c h. Okay, this is m sub c h, and then again time the change of d theta, so time m over ei and dx. So we have the virtual work equation as shown here. By the virtual work equation, what next we supposed to do? We going to determine m sub bh. Okay, we also going to go to determine the m here due to the applied loading, and also we going to determine m sub ch for this. Okay, so next we going to do what? Second, determine the equation of bending moment. That's going to be m and what? M sub bh. Okay, and m sub ch. Okay, that is our next step. Before we can go to determine the equation, okay, the equation, we're going to set the required coordinate of each member or segment, each segment of the frame. Okay, and they're going to go by the same way when we determine this m, all of the coordinate gonna be the same. Let me set this one as the x1, okay, and this one as the x2, and this one is the x3. Actually, we can set anything you like, but when you set this, every setup x1, x2, and x3 for every cases must be the same. They must be the same. Okay, and then now we are ready to determine this one. So what next then? We draw the free body diagrams and determine reactions and the required more bending moment. Okay, the first one, we start by consider this, because the m gonna involve these two equations. Now let me just take this support out before we can draw the free body diagram. We're supposed to take the support out, and then we can put the reaction into this. What happened for the first one? When the 40 kilonewton apply here, okay, if you take the moment here, you may see the 40 kilonewton will rotate in the clockwise direction, and the force here will rotate in the opposite. So let's say this is going to be B sub y gonna rotate counterclockwise, this is going to rotate clockwise, and if this B sub y is up, so there is no vertical force, so the A sub y gonna be down, and the 40 kilonewton to the right. So for this one, this is gonna be A sub x. Okay, and now we may use the equation of equilibrium. Summation of the moment about A equal to 0, and then you have the B sub y is like this. So the B sub y gonna have the moment arm from here to here of 2.4, and then the 40 gonna rotate in opposite direction equal to 40, and then you got to times 40 by 3. Now you get your B sub y equal to 120 divided by 2.4. So your B sub y gonna be equal to 50 kilonewton. Okay, this is gonna be 50 kilonewton. And now coming back here, if you do the summation of x sub x equal to 0, this one is positive in this direction, so the A sub x equal to 40 kilonewton, like this. And also if you do the summation of f sub y equal to 0, this is downward. Let's say downward is positive, so your A sub y gonna be 50 kilonewton. So you underscore it to make it. This is gonna be 50 kilonewton. This is gonna be 40 kilonewton. Now again, you draw the free body diagram of each segment. This one, the first one, is for the x1, and this for the x3, and maybe this for the x2. Okay, and you may have this is x1, this is x2, and let's say this is x2, this is x3. And when you set up the direction, of the moment, this setup gonna use for all of the small m moment. Okay, and if you have this one, summation of moment equal to 0, and then you get the force here of 50 kilonewton, and then you get the force here of 40 kilonewton. Okay, this is 40 kilonewton, and this is x1. So if you summation of moment equal to 0 here, you're gonna have m1. Okay, in this direction is positive, and 40 gonna be in opposite direction, so it's gonna equal to 40 x1. This is the first one, and this one is 50 kilonewton. And if you take the moment here, you're going to have the moment arm of x2. And let me set this is going to be the m2, summation of moment equal to 0. So your m2 is going to be equal to 50. Okay, and time x2. And the last one we have this is the b sub y here. And let's put this one as the m3, summation of moment equal to 0. So m3 is 0. Okay, that is for the moment due to the 40 kilonewton force. And then we come to this. For this one, we have 1 kilonewton here. So by this one, we may have this one as the a sub x, and this one as the b sub y, and also this one as the a sub y. If you're doing something like this, you just set up summation of moment m sub a equal to 0. Take moment about here, so b sub y again. Rotate this as a positive. Your b sub y gonna time 3. And then what we have is there is no force, so you got b sub y equal to 0. And then if you do summation of f sub y equal to 0, a sub y gonna be 0. And then if you do the summation of x sub x equal to 0, you got the a sub x equal to 1.2. So this a sub x is going to be equal to 1. And now we are ready to draw the free body diagram of each piece of this frame. Okay, this is x1, x2 and x3, and you're going to use the same. This is 1, this is m sub h bh1, this is m sub bh3, this is going to be m sub bh2 in the same direction that you set up here. And what happened is this one, that is going to be 1. If you summation of the moment here, summation of moment equal to 0. So this is in opposite direction. So this one is going to equal to x1. How about this one? This one have no force here, but it has the 1.0 here. So if you take moment here, this 1.0 gonna have this 3 meter. This 3 meter moment arm. So summation of moment equal to 0. This is gonna be 3. And again, for this, this is gonna be 1.0 again, and summation of moment equal to 0. M sub xt gonna be here, and this is gonna rotate in this direction. It's gonna be 1 times x3. So this one gonna x3. Okay, that is the next one. The last one, if you can consider here closely, this one unit assume force is in the same direction as this 40 kilonewton. So what we have is gonna be, this is gonna be equal to m divided by 40. If this m divided by 40, so we're going to have m sub c h1 equal to, you may put this one, 40 x1 divided by 40. So this is going to be equal to x1. Make it clear on this. And it's going to have this direction also. Okay. And this one, x3, you're going to have m sub c ht equal to 0. The same direction here. And for this, m sub c h2 gonna be 50x2. And then must divide it by 40. So you have this for 5x2 divided by 4. Now, that's, you have all the required moment, okay, here. And one of the best way to help you to put all this equation into this virtual work equation by using the table. Okay, we're going to draw the table. We're going to have 1, 2, 3, and 4. What we have is, we have the segment. Just put this one. This is the segment. What we have is A to C. So segment AC. From D to C, DC. And from B to D, B, D. And also you have the length. Okay, this one from 0 to 3 meter. And this one from 0 to 2.4. And this one from 0 to 3. Okay, and then what we have is the equation of the moment, m kilonewton meter. And what we have is, this is 40x1. This is going to be 50x2. And this is 0. And you have this m sub bh. That is going to be x1. This is going to be 3. And this is going to be x3. And the last one you may have is m sub ch. What we have is, this is x1, and this is going to be 5 over 4 x2, and the last one is 0. Now we are ready for the third step. We determine the displacement. What we have, displacement is going to be v sub b h and v sub c h, two of them. basis on what we have in the table. Okay, V sub BH gonna be the first one is gonna be, this is the green one, it's gonna be this one and this one, V sub BH. Okay, that means we're going to integration of 40 x1 and times x1 and now dx1 over ei, and you integrate it from 0 to 3, and next plus here. Okay, integrate from 0 to 2.4 of 50 x2, and this is gonna time 3 and dx3 over ei, and the last one here is gonna be 0 times x3, so that's gonna pass 0. Okay, now we have 40 x1 square, so it's gonna be 40 x1 cube divided by 3, and you integrate from 0 to 3 and divided by ei, so we just put this one out, 1 over ei here because they are equal, and then you plus this one gonna be 150 x2, so it's gonna be 150 x2 square divided by 2, and then you integrate it from 0 to 2.0 and then plus 0. Okay, you put everything in your calculator. You may have the first one 40 times 3 cube divided by 3, so it's going to be 40 times 9, it's going to be 360. This is going to be 75 times 2.4 square. Okay, and then you have this as the sum of 360 and 432, that is going to be 792 divided by ei, and is positive, that means it's going to be in this direction. Okay, and then you may compute the magnitude of this is going to be 492 divided by 210 power 6 kilonewton per meter square. And the I going to be 60 10 minus 6 meter power 4. So this cut this. And then you may get this of 0.066 meter, or it's going to be 66 millimeter in this direction, as you may have. So this is going to be equal to 66 millimeter. Okay, and the other one you compute V sub CH. So V sub CH gonna be, that's gonna be the time of this and this, this and this, this and this. Okay, now we have integration of 0 to 3, and we have 40x1 times x1, 40x1, and you're gonna times it by x1 and the x1 over ei. That is the first term, and then we plus this next integration of 0 to 2.4, and we have 50 x2, and it's gonna time this one 5 over 4 x2, and dx2 over ei. And the last one plus 0. Now, if you do the equation at the same as before, you will get this of 648 divided by ei. And since it is positive, the same direction as this one. Okay, and then if you put everything, it's gonna be this one divided by 260. You may get this one of 0.054 meter, or it's going to be 54 millimeter, and that's it. It's going to be in this direction. Okay, and it's going to be very easy. This one going to be 54 millimeter, and also this one, this is V sub BH is going to be 54 millimeter since this one. Okay, and for the slope, you got to determine them by putting the 1 unit moment to point A, to point C, to point D, even to point B if you like. Okay, this one also gonna have of theta sub B, and I believe these two gonna be equal. Okay, that is the end of the demonstration of showing the displacement of the frame based on the unit load method, or you may call it the moment method of virtual work. Okay, that's it.